Over 75 million years ago, a prehistoric crocodile lived in the swamps and rivers of North America during the late Cretaceous period. Measuring over 30 feet long and possessing extremely powerful jaws capable of crushing bone, this reptile, known as Deinosuchus, was a top predator of its era. Its immense size and strength were sufficient to capture and consume large dinosaurs, making it one of the most formidable creatures of its time, as evidenced by the fossil record. Why was it so furious? Before we begin the video, let us know where in the world you're watching from in the comments below, and if you enjoy learning about the prehistoric era, consider subscribing. It really helps us keep making content like this. Deinosuchus was an enormous ancient crocodile-like creature that lived during the late Cretaceous period, around 83 to 72 million years ago. Scientists still debate whether it was more closely related to modern alligators or stood as an older branch in the crocodile family tree. Either way, it was one of the most fearsome predators of its time. The story of Deinosuchus began in the 1850s, when the first pieces of its fossilized remains were unearthed in North Carolina, United States. Decades later, in the year 1909, the creature was officially given its name, Deinosuchus, which in Greek means terrible crocodile. During the 1940s, more bones were found, and scientists at the American Museum of Natural History used them to create a large model skull. Unfortunately, that early reconstruction turned out to be quite inaccurate, but it helped capture the public's imagination and introduced the world to this prehistoric giant. Even today, scientists do not have a complete picture of Deinosuchus, but discoveries of better skull fossils in recent years have revealed much more about its size, shape, and habits. Deinosuchus looked very much like a modern crocodile or alligator, but it was far, far larger. The biggest adults could reach a length of about 10.5 meters, roughly 35 feet, making them among the largest crocodilians ever known. Its teeth were thick and strong, perfect for crushing bones, and its back was armoured with heavy, rounded, bony plates called osteoderms. Studies suggest that Deinosuchus could live for as long as 50 years. Like modern crocodiles, it grew slowly, but it continued growing for a much longer time, allowing it to reach truly monstrous proportions. Fossils of this giant reptile have been discovered across 12 American states, including Texas, Montana, and several along the eastern coast. Remains have also been found in northern Mexico. In its time, Deinosuchus lived on both sides of the Great Western Interior Seaway, a vast inland sea that once divided North America in two. Along the shores of this ancient waterway, it ruled as a top predator, waiting patiently to ambush anything that strayed too close. The largest Deinosuchus individuals seem to have lived in the western regions, while the eastern populations were far more numerous. Scientists are still unsure whether these eastern and western Deinosuchus were separate species or simply regional variations of the same one. What they do agree on is that this creature could easily overpower large dinosaurs that came to the water's edge to drink. It probably also hunted sea turtles, fish, and any other animals it could catch, both in the water and on land. The scientific story of Deinosuchus began in the year 1858, when geologist Ebenezer Emmons discovered two massive fossil teeth in Bladen County, North Carolina. At first, he thought they belonged to a marine reptile called Polyptychodon, which he believed to be crocodile-like. He even gave the teeth a new species name, Polyptychodon rugosus. Only later did researchers realize that Polyptychodon was actually a pliosaur, an entirely different kind of sea reptile. In truth, those teeth were most likely the first known remains of Deinosuchus. In 1869, another scientist, Edward Drinker Cope, described a similar large tooth found in nearby Sampson County. He named it Polydectes biturgidus, but again, it almost certainly came from Deinosuchus. Then, in the year 1903, fossils of strange dome-shaped bony plates were found lying on the surface near Willow Creek, Montana. They were discovered by John Bell Hatcher and T.W. Stanton, who at first thought the fossils came from a heavily armoured dinosaur called Euplocephalus. However, when more bones were dug up, including ribs, vertebrae, and part of a pelvis, it became clear that they belonged to a giant crocodilian, not a dinosaur. Hatcher reportedly lost interest after hearing that, but after his death in 1904, his colleague W. J. Holland studied the fossils more carefully. In 1909, Holland officially named the new animal Deinosuchus hatcheri, in honour of Hatcher himself. A major step forward came in 1940, when an expedition from the American Museum of Natural History found more fossils of giant crocodilians in what is now Big Bend National Park, Texas. These remains were described in 1954 by scientists Edwin H. Colbert and Roland T. Bird, who at first named the animal Phobosuchus riograndensis. Later research by Donald Baird and Jack Horner proved that these fossils actually belonged to Deinosuchus, a conclusion that modern scientists widely accept. At the museum, Colbert and Bird used the fragments to create a life-sized model of the skull, based on the shape of a modern Cuban crocodile. They called it a conservative estimate, noting that the real skull might have been even longer if they had used a saltwater crocodile as a reference. Because they didn't yet know that Deinosuchus had a broad, short snout, their model ended up being far too long and wide. Still, this reconstruction became famous. It was displayed for years and introduced Deinosuchus to generations of visitors who gazed up at its enormous jaws in awe. Over the following decades, many more fossils were found, though most were small and incomplete. Even so, these discoveries helped map out where Deinosuchus once lived and showed how widespread it truly was. As paleontologist Chris Brochu once joked, even a handful of bone granola was enough to confirm Deinosuchus's presence, since its bony armor plates were so distinctive. By the early 2000s, better skull fossils had allowed paleontologist David R. Schwimmer to digitally reconstruct about 90% of the animal's skull, bringing scientists closer than ever to understanding the full scale of this ancient monster. In the year 1954, based on the shape and structure of its teeth, Deinosuchus was placed in the crocodile family Crocodilidae. However, as time went on and more fossils were uncovered, particularly new specimens from Texas and Georgia in 1999, this early assumption began to change. Detailed studies of these fossils showed that Deinosuchus was actually more closely related to alligators, placing it within a group called Alligatoroidea, alongside a genus named Ladiosuchus. This view gained further support in the year 2005, when paleontologists discovered an exceptionally well-preserved brain case of Deinosuchus in the Blufftown Formation of Alabama. Its internal structure revealed several similarities to that of the modern American alligator, yet it was clear that Deinosuchus was not a direct ancestor of today's alligators. It was more like a powerful ancient cousin. Since the revival of the name Deinosuchus in 1979, scientists have traditionally recognized two main species, Deinosuchus rugosus from the ancient landmass of Appalachia, and the larger Deinosuchus hatcheri or Deinosuchus riograndensis from Laramidia, the western part of North America. These forms were said to differ in the shape of their bony armor plates, called osteoderms, and teeth. But over time, as more fossils were compared, the supposed differences between them began to blur. Many researchers started to believe they might actually represent a single, widespread species that simply varied in size. In 2013, a team led by Ermis studied Deinosuchus fossils from Utah's Kaiparowitz Formation and argued that D. rugosus was too poorly defined to be valid, since its original teeth lacked unique features. They suggested using the name Deinosuchus hatcheri for material found in western North America, and noted that the skull material from the eastern region, Appalachia, was still poorly described. 7 years later, in 2020, paleontologists Cosette and Brochu re-examined the issue and agreed that D. rugosus should be considered a nomen dubium, a doubtful name. They introduced a new species from Appalachia, Deinosuchus schwimmeri, named in honor of paleontologist David R. Schwimmer. Some fossils that had once been called D. rugosus were reassigned to this new species. Because the original Deinosuchus hatchery fossils were incomplete, the researchers proposed transferring the official type species designation to the better preserved Deinosuchus riograndensis to make classification clearer. Even more recently, in a 2025 study, Jules D. Walter and his team suggested something even more surprising. Their analysis showed that many traits once thought to be unique to alligator relatives were actually widespread among ancient crocodilian ancestors. As a result, Deinosuchus might not have been a true alligatoroid, or even a true crocodilian at all. Instead, it could represent a more primitive kind of Eusuchian, an early branch of modern crocodiliforms that split from the main crocodile lineage after Ladiosuchus, but before the land-dwelling Planocronidae. Despite its monstrous size, Deinosuchus probably looked very much like today's crocodiles and alligators. It had a broad, alligator-like snout with a slightly swollen tip. Each premaxilla, the front part of the upper jaw, held 4 teeth, the first pair being noticeably smaller than the rest. The main upper jaw bones, or maxillae, contained about 21 or 22 teeth each, while the lower jaws carried at least 22. The teeth were thick and sturdy, especially near the back of the mouth where they were short, blunt and rounded, perfect for crushing prey rather than piercing it. When the creature's mouth was closed, only one lower tooth on each side would have been visible. Its skull had an inflated shape around the nostrils, with two strange openings at the front of the snout, features seen in no other crocodilian, the purpose of which remains a mystery. Like modern crocodiles, Deinosuchus had a secondary bony palate, allowing it to breathe through its nostrils even while lying almost completely submerged. Its backbone was made of special ball-and-socket joints called procoelous vertebrae, an advanced feature also seen in today's crocodilians, giving flexibility and strength to its powerful body. Its back was armoured with enormous, heavily pitted osteoderms, thick rounded plates that acted like shields. The deep grooves on these plates once held strong connective tissue, forming a network of support across its back. These reinforcements helped Deinosuchus carry its enormous weight, even when it hauled itself out of the water, suggesting it could move on land in much the same way as modern crocodiles do. For decades, scientists have debated exactly how large Deinosuchus could grow. Early reconstructions in 1954, based on a skull about 1.5 meters long and a lower jaw nearly 2 meters long, estimated a total body length of about 15 meters, nearly 50 feet. However, later research revealed that this was an overestimate. More accurate measurements made in 1999 suggested typical lengths of 8 to 10 meters, between 26 and 33 feet, and weights between 2 and 5 metric tons. Some fossils, such as a skull from Texas measuring about 1 1/3 meters long, indicate individuals roughly 10 meters in total length. Paleontologist David Schwimmer later proposed that the very largest Deinosuchus riograndensis individuals might have reached 12 meters, about 39 feet, and weighed around 8.5 metric tons. A massive lower jaw fragment discovered later supported this, belonging to an animal with a skull nearly 1.5 meters long and a total length of over 10 meters. These giants would have rivaled or even surpassed the size of most living crocodilians. For comparison, the modern saltwater crocodile, Crocodylus purussaurus, holds the record for the strongest bite of any living animal, with forces reaching over 16,000 newtons in an individual about 4.5 meters long. The bite force of Deinosuchus, however, has been estimated at anywhere from 18,000 to more than 100,000 newtons, many times stronger than that of any animal alive today. Although it might not have been the single largest crocodiliform ever, other prehistoric monsters like Purussaurus, Sarcosuchus, and Champsosaurus may have been similar in scale. Deinosuchus still stands as one of the most fearsome predators ever to inhabit the rivers and swamps of ancient North America, a true, terrible crocodile that could challenge even the dinosaurs themselves. During the middle of the 20th century, scientists began to imagine the terrifying role that Deinosuchus, the terrible crocodile, must have played in its ancient world. In the year 1954, paleontologists Edwin H. Kolber and Roland T. Bird boldly suggested that this massive reptile may very well have hunted and devoured some of the dinosaurs with which it lived. Only a few years later, in 1961, Kolber restated the idea with even greater confidence. He declared that such an enormous creature could hardly have been anything other than a dinosaur hunter. In his words, certainly this crocodile must have been a predator of dinosaurs. Otherwise, why would it have been so overwhelmingly gigantic? It hunted in the water where the giant theropods could not go. Decades later, in the year 2002, David R. Schwimmer discovered fossil evidence that added real weight to this thrilling idea. Several tailbones of duck-billed dinosaurs, known as hadrosaurs, found near Big Bend National Park in Texas, bore deep bite marks matching the teeth of Deinosuchus. This suggested that the monster crocodile had indeed attacked and eaten dinosaurs, at least on some occasions. The following year, in 2003, Christopher Abroshu supported this theory, remarking that Deinosuchus probably dined on ornithopods from time to time. Like modern crocodiles, Deinosuchus is believed to have been a patient and deadly ambush predator. It likely waited quietly at the water's edge, nearly invisible beneath the surface, before exploding into motion to seize an unsuspecting dinosaur or land animal. Once caught, the victim would have been dragged underwater until it drowned. A study published in the year 2014 even suggested that Deinosuchus could perform a death roll, the same spinning maneuver that modern crocodiles use to tear apart their prey. More fossil evidence came to light in 2010, when a leg bone of a tyrannosauroid dinosaur found in New Jersey and kept in the New Jersey State Museum was discovered to bear tooth marks, possibly the work of a Deinosuchus. Interestingly, Schwimmer and G. Dent Williams had earlier proposed in 1996 that this ancient reptile also preyed on large sea turtles. The back teeth of Deinosuchus were broad and flat, perfect for crushing hard shells. In its eastern habitats, the side-necked turtle Bothromis was especially common, and many of its shells were found marked by large bites that likely came from Deinosuchus itself. According to Schwimmer's later conclusions in 2002, Deinosuchus did not feed the same way everywhere it lived. The smaller individuals in eastern North America behaved much like modern American alligators, eating whatever they could catch, including turtles, large fish, and smaller dinosaurs. The larger Deinosuchus of Texas and Montana, however, seem to have been more specialized hunters, capable of bringing down even the biggest dinosaurs that came too close to the water. In the eastern regions, where no large theropod dinosaurs were known to exist, Deinosuchus would have been the apex predator, ruling its environment without rival. In 1999, researchers Gregory M. Erickson and Christopher A. Brochu conducted an important study of the creature's growth. By studying growth rings in the bony plates, or osteoderms, found along Deinosuchus's back, they estimated that these giants grew at a similar rate to modern crocodiles, but continued growing for a far longer time. A Deinosuchus may have needed more than 35 years to reach full size, and the oldest individuals might have lived for over 50 years. Unlike the fast-growing, short-lived dinosaurs, a full-grown Deinosuchus could have witnessed several generations of dinosaurs come and go in its lifetime. However, Schwimmer noted that these conclusions depended on the assumption that each growth ring represented 1 year, just as they do in living crocodiles. But this might not have always been the case. The growth patterns could have been influenced by many factors, such as seasonal climate changes, food availability, or migrations of prey animals. If the rings formed twice per year rather than once, Deinosuchus would have grown faster than previously thought, with a lifespan more similar to that of modern crocodilians. Fossils of Deinosuchus have been discovered across a wide area on both sides of the ancient Western Interior Seaway, a vast inland sea that once split North America. Remains have been found in 12 states, including Utah, Montana, Wyoming, New Mexico, New Jersey, Delaware, Georgia, Alabama, Mississippi, Texas, and the Carolinas. In 2006, an additional fossil from northern Mexico expanded its known range even further. A possible scute from Colorado has also been reported. The richest collections of fossils come from the Gulf coastal plain region of Georgia, near the border with Alabama. All known remains of Deinosuchus date from the Campanian stage of the late Cretaceous period, between about 82 and 73 million years ago. These fossils reveal that the creature favoured estuarine environments, where rivers meet the sea. In places such as the Aegisuchus Formation of Texas, where the largest individuals have been found, Deinosuchus probably lived in brackish water bays. Some remains have been discovered in marine sediments, but it is uncertain whether the animal actually ventured into the open ocean like modern saltwater crocodiles, or if the bodies were carried there after death. Deinosuchus was one of the most formidable animals of its time, an unmistakable presence in the southern ecosystems of late Cretaceous North America. Its very existence may explain why few large theropod dinosaurs lived in the region known as Appalachia, because in those swampy coastal plains, Deinosuchus reigned supreme as the top predator, a silent ruler of both water and shore. Sarcosuchus was an enormous ancient reptile that lived long before humans walked the earth. This mighty creature existed during the early part of the Cretaceous period, from about 130 to 112 million years ago, in regions that are now parts of Africa and South America. It belonged to a group of crocodile-like reptiles called crocodiliforms, and was among the largest of them all, so massive that it dwarfed even the biggest crocodiles alive today. The largest known species, Sarcosuchus imperator, could grow up to around 9 to 9.5 meters long, about the size of a large bus, and weigh as much as between 3.5 to over 4 metric tons. It was an apex predator of its time, and many scientists believe that almost nothing on land or in the water could challenge it. There were 2 known species, Sarcosuchus imperator from what is now Niger in Africa, and Sarcosuchus harti from northeastern Brazil. Fossil fragments have also been discovered in Morocco, Tunisia, and possibly even Libya and Mali, suggesting that these giant reptiles roamed across much of the ancient southern continents. The story of its discovery began in the mid-20th century. Between the years 1946 and 1959, the French paleontologist Albert Félix de Lapparent led several expeditions into the Sahara Desert. There, his team unearthed bits and pieces of Sarcosuchus fossils, parts of skulls, backbones, teeth, and bony plates called scutes. These early finds hinted at a creature of immense size but left much unknown. In 1964, a nearly complete skull was uncovered in Niger by the French Atomic Energy Commission. Yet, it wasn't until the late 1990s that Sarcosuchus truly came into the spotlight. In 1997 and again in 2000, American paleontologist Paul Sereno led expeditions that found 6 new specimens, including one with about half of its skeleton preserved, finally giving scientists a clearer picture of this prehistoric monster. Sarcosuchus was only a distant relative of modern crocodiles, but it shared many familiar traits. Adults could reach up to 9 meters in length and weigh several tons. Its skull was especially remarkable, with a long snout making up about 3/4 of its total head length. It had 35 teeth on each side of its upper jaw and 31 on each side of its lower jaw. The upper jaw extended farther than the lower one, creating a slight overbite when its mouth was closed. Young Sarcosuchus individuals had a slender, elongated snout, much like the living gharial of India, but as they matured, their snouts broadened, giving them a more powerful bite suited for tackling large prey. One of the most unusual features of Sarcosuchus was a bulging structure at the end of its snout called a bulla. It resembled the gara found in modern male gharials, but unlike the gharials, the bulla appeared in every Sarcosuchus skull discovered so far. This suggests it was not a feature limited to males. Scientists are still unsure of its exact purpose. It may have played a role in sound production, water movement sensing, or even communication. Its back was covered in thick bony plates called osteoderms, forming a continuous shield from its neck down to the middle of its tail. This armour was similar to that of other ancient crocodile-like reptiles, such as Goniopholis and Deinosuchus. Modern crocodiles, by contrast, have gaps between the bony plates on their necks and bodies, showing how much Sarcosuchus still retained features from its more primitive ancestors. Since no complete skeletons have been found, scientists had to estimate its size using the skull length, a method also used for modern crocodiles. Paul Sereno and his team in 2001 compared the skull of Sarcosuchus with those of living gharials from India and saltwater crocodiles from Australia. Based on these studies, they estimated that the largest skull, measuring about 1.5 meters from the snout to the back of the head, belonged to an animal over 11.5 meters long and weighing as much as 8 metric tons. This would have made Sarcosuchus one of the biggest crocodile-like reptiles to ever live, even larger than other prehistoric giants like Deinosuchus, Champsosaurus, and Purussaurus. However, later studies suggested that Sereno's estimates were slightly too high. In 2019, new research by O'Brien and colleagues used more precise comparisons of skull and body proportions. Their calculations indicated that the largest Sarcosuchus imperata individuals were around 9 to 9.5 meters long, with a body mass between 3.5 and just over 4 metric tons. Even with these smaller numbers, Sarcosuchus was still an extraordinary giant, a predator that could have dragged dinosaurs into the water and ruled the ancient rivers with unmatched power. Sarcosuchus, whose name means flesh crocodile, belonged to an ancient group of crocodile-like reptiles called the Phylodosauridae. These creatures were relatives of modern crocodiles, alligators, and gharials, but they lived outside the true crocodilian family. Within this group, Sarcosuchus was most closely related to another genus found in North America called Terminonaris. Most members of this ancient family had long, thin snouts and spent their lives in the water, adapting to various aquatic environments. Some of them could survive in salty seas, while others, like Sarcosuchus, lived mainly in freshwater rivers and lakes. The earliest and most primitive of these reptiles seem to live in coastal regions where rivers met the sea, thriving in places where saltwater and freshwater mixed together. What made Sarcosuchus particularly interesting was that it was not as picky as many of its relatives when it came to food. While most phylodosaurids mainly ate fish, Sarcosuchus was more of a generalist predator. It likely hunted whatever it could overpower, from large fish to land animals that ventured too close to the water. A scientific study published in the year 2019 even suggested that Sarcosuchus was more closely related to another group of ancient crocodile-like reptiles known as Dirosauridae, placing it further along the evolutionary branch called Tethyssuchia. The story of Sarcosuchus begins in the mid-20th century, when a series of expeditions were carried out across the Sahara Desert between the years 1946 and 1959. These explorations were led by the French paleontologist Albert Félix de Lapparent, who unearthed several massive fossils of crocodile-like creatures from a geological layer called the Continental Intercalaire Formation. Some fossils were discovered in Fougera Bendrao in Mali and near the Algerian town of Oulef. These finds were informally called the Oulef crocodile. Other remains were recovered from the Enelgeta Formation in southern Tunisia, including parts of skulls, teeth, bony plates called scutes, and vertebrae. In the year 1957, another paleontologist, H4, found several enormous teeth in what is now known as the Elrez Formation. When these fossils were later examined by the French paleontologist Frans de Bruyne, they were recognized as belonging to a giant crocodile with a very long snout. Then, in the year 1964, a research team from the French Atomic Energy Commission made a major discovery in the Gadoufawa region of Niger, an almost complete skull. This skull was sent to Paris for study, and 2 years later, in 1966, it became the type specimen for a new genus and species, Sarcosuchus imperator, meaning flesh crocodile emperor. More than a decade later, in 1977, another species of Sarcosuchus was identified, Sarcosuchus harti, from fossils found in northeastern Brazil. These remains had actually been discovered much earlier, in the year 1867, by the American naturalist Charles Hart. He had sent 2 teeth to the famous paleontologist Othniel Charles Marsh, who originally named them Crocodilus harti. Later, in 1907, these fossils were reclassified under another genus, Goniopholis harti. But when scientists examined them again in the 20th century, they realized the fossils actually belonged to Sarcosuchus. Today, the jaw fragment, scute, and teeth of S. harti are preserved in the British Museum of Natural History. The next major discoveries came when American paleontologist Paul Sereno led expeditions to the Sahara in the mid-1990s. His team explored regions such as the Ofu Formation in Morocco in 1995 and later the Elrez Formation in Niger in 1997 and 2000. They recovered partial skeletons, several skulls, and about 20 tons of additional fossils from rocks dating back to roughly 112 million years ago, during the early Cretaceous period. Preparing and studying these remains took nearly a full year. Other fossils attributed to Sarcosuchus have been found in several parts of North Africa, including tooth fragments from the Efezouan Formation in Morocco and possible remains from northwestern Libya. In 2018, additional fossils, including teeth, vertebrae, and parts of the skeleton were discovered in Tunisia's Oumed Diab member, providing more evidence of this giant reptile's widespread presence. To understand how Sarcosuchus grew, Sereno and his team examined thin sections of its bony armour, or osteoderms, from a young adult estimated to be about 80% of its full-grown size. They counted roughly 40 growth lines in the bones, similar to the rings in a tree, and concluded that Sarcosuchus reached adulthood after about 50 to 60 years. This was far longer than modern crocodiles, which rarely live that long in the wild. Sereno suggested that Sarcosuchus grew to its enormous size by staying in a rapid growth phase for a much longer time than today's crocodilians. Interestingly, scientists think a similar growth pattern occurred in another giant prehistoric crocodile, Deinosuchus. When comparing the skull of Sarcosuchus with that of living crocodiles, researchers noticed that its snout was much broader and its teeth did not interlock as tightly. This suggested that, unlike narrow-snouted crocodiles that specialize in catching fish, Sarcosuchus likely had a more varied diet, similar to the modern Nile crocodile. It probably ate both aquatic and land animals, including the dinosaurs that shared its habitat. However, a biomechanical study conducted in 2014 revealed something surprising. It suggested that Sarcosuchus might not have been able to perform the famous death roll maneuver, where modern crocodiles twist their bodies to tear apart their prey. This means that if Sarcosuchus hunted large animals, it probably used a different method to subdue them. The fossils of S. imperator were found in the region of Gadoufawa, in the Elruz Formation of Niger's Ténéré Désert. Around 112 million years ago, this region was not a barren desert, but a lush, tropical river system filled with life. While the land nearby swarmed with dinosaurs such as the plant-eating Allodaposuchus and Uranosaurus, as well as long-necked giants like Nigersaurus, there were also several predators, including the sail-backed Suchomimus, the massive Eocarcharia, and the smaller but fierce Cryptops. Isotope studies of the fossils suggest that Sarcosuchus fed on both fish and dinosaurs. The chemical makeup of its bones indicates that about 58% of its diet came from fish, while the rest was made up of land animals, probably those unlucky enough to wander too close to the riverbanks. Meanwhile, Sarcosuchus harti lived in what is now Brazil, in the Recôncavo Basin, during roughly the same period. Its environment was a shallow lake system filled with similar fish species, including Lepidotus and two kinds of Mawsonia. Although dinosaur remains in that region are scarce and fragmentary, scientists have found evidence of both meat-eating and plant-eating types living alongside this ancient crocodile. Purussaurus was a truly gigantic ancient caiman that once ruled the rivers and swamps of South America during the Miocene epoch, which began about 23 million years ago and ended roughly 5 million years ago. This enormous reptile lived through the Frisian to the Huayquian ages, according to the South American land mammal age system. Its fossils, mostly consisting of skulls, have been uncovered in several regions, from the dense jungles of Brazil and Peru to Argentina, Colombia, Panama, and the northern plains of Venezuela. Each discovery reveals more about this monstrous predator that once dominated its tropical world. The largest known skull of the type species, Purussaurus brasiliensis, measured about 1.5 meters, around 57 inches, long. From this, scientists have estimated that the living animal could have grown to about 10 meters in length, or roughly 34 feet, and weighed more than 5 metric tons. Some researchers, however, have suggested that the biggest individuals might have reached up to 12 meters long, around 40 feet, and weighed as much as 8 metric tons. According to these studies, such a beast would have needed an enormous amount of food every day, perhaps around 40 kilograms, or about 90 pounds of meat. Other estimates are slightly smaller, suggesting lengths of about 11 meters and weights of roughly 5.5 metric tons. More recent studies published in the year 2022 offered somewhat different results. Using comparisons with other related species, they suggested that Purussaurus might have measured between 7 and 9 meters long, with a body mass between 2 and 6 metric tons. Another approach that did not rely on family relationships gave slightly larger results, around 9 to 10 meters in length and close to 4 or 5 metric tons in weight. Because only skulls have been found so far, no one knows for sure how long Purussaurus truly was. Its bite, however, is easier to imagine. Scientists have calculated that it could close its jaws with a force of more than 50,000 newtons, about 5 metric tons of pressure, and perhaps even as high as 69,000 newtons, equal to 7 metric tons of crushing power. With such strength, Purussaurus would have been the uncontested top predator of its world. It could have attacked and eaten almost anything that crossed its path, giant mammals, turtles, or even other reptiles. No smaller carnivore of the time could challenge it. Yet, the same immense size that made Purussaurus so powerful may also have led to its downfall. As the climate and landscape of South America changed over millions of years, the great rivers and wetlands that sustained it began to disappear or shift. Smaller and more adaptable caimans survived these changes, but the over-specialized Purussaurus could not adjust quickly enough and eventually vanished from the earth. The skeleton of another species, Purussaurus mirandae, shows that it was specially built to carry its massive body. Unlike modern crocodiles and alligators, which have 2 sacral vertebrae, the bones connecting the spine to the pelvis, P. mirandae had 3, a rare adaptation that likely helped support its immense weight and gave its limbs a more upright stance. The teeth of Purussaurus were also remarkable. They measured about 5 centimeters, roughly 2 inches, in length and were slightly curved backward, with small ridges running along their edges. These ridges, similar to those seen in Ziphodont teeth, were perfect for gripping and tearing the flesh of large animals. The front teeth were tall and sharply pointed, while those at the back were shorter and more rounded, allowing them to crush bones without breaking easily. Purussaurus ranks among the largest crocodiliforms ever known, standing alongside ancient giants like Sarcosuchus, Deinosuchus, and Ramphosuchus. Sarcosuchus and Deinosuchus lived much earlier, during the Cretaceous period, while Ramphosuchus lived around the same time as Purussaurus but in India, and had a longer, narrower snout more like that of a modern gharial. Some studies even suggest that Purussaurus was heavier than both Sarcosuchus and Deinosuchus, because of its wider and shorter skull, which required a thicker, more muscular neck to hold up its massive head. In the summer of the year 2005, a joint French-Peruvian expedition known as the Fitzcarrald Expedition uncovered new fossils of Purussaurus in the Peruvian Amazon, about 600 kilometers away from Lima. Later, biomechanical studies of its skull showed that Purussaurus was capable of performing the infamous death roll, the violent spinning motion modern crocodiles use to tear apart their prey. All of its main sensory organs, the eyes, ears and nostrils, were positioned on the top of its skull just like in living caimans. This feature allowed Purussaurus to hide almost completely beneath the water's surface, silently waiting for an unsuspecting animal to come close before striking with terrifying speed. Purussaurus, the gigantic prehistoric caiman, likely had a diet as fearsome and varied as its enormous size suggested. It probably hunted or scavenged a wide range of creatures, from massive turtles like the extinct Stupendomes to other crocodilians such as Carnufex, Diplocynodon, and Purussaurus. It may have also preyed upon birds like the anhinga and an array of mammals, including slow-moving sloths, bats, and giant rodent relatives of the modern capybara, such as Josephortagasia, which could weigh up to 700 kilograms, 1,540 pounds. Among its potential prey were also primates like Stetonia and even river dolphins, making clear that Purussaurus ruled both land and water. The habitats of Purussaurus were diverse and rich, including rivers, floodplains, and lakes. In Venezuela, the species P. mirandae shared its environment with a wide variety of creatures, from marine and freshwater fish to turtles, crocodilians, and both terrestrial and aquatic mammals. Its world was tropical and coastal, filled with life in every corner. Earlier in Colombia, P. nivensis roamed alongside an astonishing variety of animals. Giant astropotheres, such as Granostrepitherium and Xenostrepitherium, lumbered across the land, while the first forms of Murasuchus and Diplocynodon patrolled the waterways. Terrestrial crocodiliforms like Langstonia also shared this prehistoric landscape. Fossil evidence even shows bite marks on the tibia of a Phorus racid, a giant flightless bird which matched the jaws of a caiman, possibly a young Purussaurus. Whether this represents a daring hunt or scavenging remains unknown, but it hints at the predator's immense power. The fauna of this region lived around 13 million years ago during the Laventon stage of the late Miocene. The name Purussaurus itself comes from the Purus River, the place where its first fossils were discovered, forever linking this enormous predator to the waterways it once ruled. Dakosaurus, an ancient and terrifying creature of the seas, was a giant marine crocodilomorph that belonged to a family of specialized sea-dwelling crocodile-like reptiles known as Metriorhynchidae. It lived during a time that spanned the later portion of the Jurassic period and reached into the early part of the Cretaceous period, a stretch of history that spanned tens of millions of years when the Earth's oceans were ruled by formidable predators. Dakosaurus was not just any crocodilomorph. It was one of the fiercest hunters to ever glide through the warm prehistoric seas. Its body was sleek, designed to cut through water with incredible agility, and its teeth were a perfect weapon, serrated like the edge of a tiny saw, yet flattened from side to side, making them ideal for slicing through the flesh of any creature unlucky enough to be caught in its jaws. These adaptations, combined with its powerful swimming ability, made Dakosaurus an apex predator, the kind of animal that dominated its ecosystem, shaping the lives and behaviors of every other marine species around it. The name Dakosaurus itself tells a story of fear and fascination. It comes from the Greek words dakos, meaning biter, and sauros, meaning lizard, which together translate to biter lizard. This name was chosen with intent, to highlight the creature's formidable teeth and hunting prowess. Paleontologists who studied this genus were struck by how perfectly its anatomy reflected its predatory lifestyle, and even today, the name conjures images of a relentless predator tearing through the waves with deadly efficiency. The tale of Dakosaurus's discovery is as intriguing as the animal itself. The first fossil evidence emerged in the mid-19th century, a time when paleontology was beginning to capture the imagination of scientists and the public alike. In the year 1846, a German paleontologist named Theodor Pleininger uncovered a single tooth, which he at first believed belonged to a species of Geosaurus. He named it Geosaurus maximus, thinking he had found yet another example of a giant marine reptile already known to science. However, a decade later, in the year 1856, Friedrich August von Quenstedt examined this tooth more closely and realized it represented something far more extraordinary. He recognized that it belonged to a completely new genus, and thus Dakosaurus was formally introduced to the scientific world. Von Quenstedt explained that he chose the name to emphasize the creature's fearsome bite, remarking in his writings that few creatures could match its terrifying teeth. He even went so far as to describe Dakosaurus as one of the most fearsome predators one could imagine, a statement that would prove accurate as more fossils came to light. As the years passed, additional fossils of Dakosaurus were uncovered across Europe and beyond, revealing the wide reach of this marine predator. Some of its teeth were so large and intimidating that early paleontologists mistakenly thought they belonged to giant theropod dinosaurs such as Megalosaurus. In the year 1871, Emanuel Bunzel reported remains that had originally been called Megalosaurus schneitimi, but modern research now identifies these fossils as belonging to Dakosaurus maximus. Fossils attributed to Dakosaurus have been discovered across a wide geographic range, including England, France, Switzerland, Germany, Poland and Russia, with surprising finds as far away as Argentina and Mexico. The European specimens include some teeth that date back to the Oxfordian stage, indicating that ancestors of Dakosaurus were already prowling the seas earlier than previously believed. These discoveries have helped paleontologists understand not only the physical characteristics of Dakosaurus, but also its distribution and ecological significance. One particularly fascinating species, Dakosaurus andiniensis, carries a name that captures both its ferocity and its geographical origins. Its name means biter lizard from the Andes, reflecting the location of its discovery in the Neuquén Basin of Argentina, a region renowned for its abundant and diverse fossil beds. The first report of this species came in the year 1985, and it was formally described in the year 1996. Dakosaurus andiniensis stood out among marine crocodilomorphs for its unusually short, deep and tall snout, a feature that earned it the playful nickname Godzilla in popular press reports. Its fossils date from the late Jurassic into the early Cretaceous, approximately spanning the late Tithonian to the early Berriasian stages. This species provides a glimpse into the incredible diversity within the Dakosaurus genus and demonstrates how evolutionary pressures in different marine environments could lead to unique adaptations even within a single family of marine predators. Other species of Dakosaurus, such as Dakosaurus nikiensis, were initially misidentified as dinosaurs, a confusion that highlights how challenging it can be to classify fragmentary remains from deep time. Later research revealed that these creatures were indeed marine crocodilomorphs, though the preservation of some fossils has left their exact identity uncertain. In Mexico, paleontologists have uncovered incomplete skulls in rocks dating to the Kimmeridgian stage, yet these specimens have not been confidently assigned to a particular species. Each new discovery adds layers of complexity to the story of Dakosaurus, illustrating how this genus occupied a range of habitats and evolved distinct traits across time and geography. All known Dakosaurus species shared a number of remarkable physical traits. They were large, typically measuring 4 to 5 meters in length, which translates to roughly 13 to 16 feet. Their bodies were streamlined, built for speed and agility in the water. Unlike modern crocodiles, Dakosaurus had finned tails that acted like powerful propellers, allowing it to glide through the oceans with minimal resistance. Its teeth were both serrated and flattened, a combination rarely seen in other marine crocodilomorphs and considerably larger than those of its relatives. These adaptations made it an apex predator, capable of preying on a variety of marine animals and defending its dominance against any challenger. The skull of Dakosaurus was triangular in shape, with large openings known as supratemporal fenestrae that anchored massive jaw muscles. These features allowed it to deliver an extraordinarily strong bite, enabling it to seize and tear apart prey with ease. Its deeply rooted teeth and robust jaws, coupled with the ability to twist its head while feeding, meant Dakosaurus could inflict damage much like a modern killer whale, tearing chunks of flesh from its prey with brutal efficiency. One of the most well-known species, Dakosaurus maximus, has been discovered in the famous Solnhofen limestone of Bavaria, Germany. These rocks date to the early Tithonian stage of the late Jurassic, a period when the seas were teeming with life. In this environment, Dakosaurus and its close relative Geosaurus giganteus likely held the position of top predator, hunting other large marine animals. Smaller marine crocodilomorphs, such as Cricosaurus elegans, Rachiosaurus gracilis, and the teleosaurid Aeolodon, primarily preyed on fish, highlighting a clear ecological division. Similarly, in the slightly older Nusplingen limestone of southern Germany, Dakosaurus again appears as the dominant predator, living alongside fish-eating species like Cricosaurus suevicus. These fossil sites paint a vivid picture of the marine ecosystems of the late Jurassic, showing how Dakosaurus and its relatives shaped the structure of the food web. Despite its dominance in the oceans, many aspects of Dakosaurus's life remain shrouded in mystery, particularly its reproductive habits. Scientists have not yet found eggs or nests, leaving unanswered questions about whether Dakosaurus came ashore to lay eggs like modern turtles, or gave birth to live young in the ocean, similar to dolphins or the ancient ichthyosaurs. Its body, however, was perfectly adapted for life in the open sea, suggesting that Dakosaurus was likely a fully marine animal, capable of long-distance swimming, hunting in deep waters, and surviving in a vast and dynamic oceanic environment. Its streamlined form, powerful tail, and specialized teeth all point to a life spent chasing prey beneath the waves, a life where only the strongest and most agile could survive. The story of Dakosaurus is not only a story of a predator, but also a story of scientific discovery, mistaken identity, and the gradual unveiling of nature's complexity over millions of years. The first fossil tooth discovered in 1846 set in motion decades of research, debate, and eventual understanding that this creature represented something entirely new. Over the next century and a half, more fossils were uncovered across Europe and the Americas, each adding detail to the picture of a predator perfectly suited to its time and place. From Germany to Argentina, Dakosaurus left traces of its existence in rocks that would endure for tens of millions of years, waiting to be found by curious paleontologists. Fossil evidence shows that Dakosaurus was part of a remarkable radiation of marine crocodilomorphs during the late Jurassic and early Cretaceous, a period when the oceans were dominated by reptiles, many of them terrifying in their size, strength, and hunting abilities. Within this group, Dakosaurus was unique. While other species had long, narrow jaws ideal for catching fish, Dakosaurus had evolved shorter, deeper, and more robust jaws capable of handling larger prey. This meant it could tackle animals that other marine crocodilomorphs could not, securing its position at the top of the food chain. Its combination of strength, agility, and specialized teeth made it an ideal predator, able to seize fish, smaller marine reptiles, and perhaps even other predators if the opportunity arose. The discovery of Dakosaurus andiniensis in Argentina expanded the known diversity of this genus, showing how these predators adapted to different environments. The Neuquén Basin, where this species was found, is renowned for its rich fossil beds, which have preserved an astonishing variety of life from the late Jurassic and early Cretaceous. The short and tall snout of Dakosaurus andiniensis is one of the most striking features among marine crocodilomorphs, illustrating how evolution could produce unusual and highly specialized adaptations in response to ecological pressures. Meanwhile, other species, like Dakosaurus nicayensis and the Mexican specimens, demonstrate that Dakosaurus was widespread and successful across different parts of the world, from Europe to the Americas. The size and power of Dakosaurus made it a formidable force. Measuring 4 to 5 meters in length, it could move with surprising speed and agility in the water, aided by a powerful finned tail that acted like a natural propeller. Its teeth, some of which were serrated and flattened, were tools designed to tear and slice, giving Dakosaurus an advantage over prey that might have seemed too large or too quick for other predators. Its triangular skull, deeply rooted teeth, and strong jaw muscles allowed it to twist and manipulate its prey, a hunting strategy that would have been terrifying to witness. Modern predators, such as killer whales, use similar techniques to subdue prey, but Dakosaurus did this tens of millions of years ago, long before mammals had taken over the oceans. The ecological role of Dakosaurus was crucial in shaping marine communities. As a top predator, it controlled the populations of smaller marine reptiles and large fish, creating a balance in the food web. Fossils from the Solnhofen and Nusplingen limestones reveal how Dakosaurus coexisted with other marine crocodilomorphs, each occupying a distinct ecological niche. While Dakosaurus hunted larger prey, smaller relatives focused on fish, showing a division of labour among predators that reduced competition and allowed multiple species to thrive in the same environment. These interactions paint a dynamic and vivid picture of late Jurassic seas, teeming with life and punctuated by dramatic predator-prey encounters. Although much is known about its anatomy and fossil distribution, Dakosaurus remains enigmatic in certain respects. Its reproduction is a mystery, as no eggs or nesting sites have been discovered. Scientists debate whether it returned to land to lay eggs like turtles or gave birth to live young in the water. This uncertainty leaves an open question about how fully marine Dakosaurus really was, but its body suggests it was well equipped to live entirely at sea. Its streamlined shape, powerful tail, and specialized teeth are all adaptations that allowed it to thrive in a challenging and competitive marine ecosystem, where survival demanded speed, strength, and cunning. From the first tooth found in 1846 to the formal description by von Quenstedt in 1856, and through subsequent discoveries across Europe and the Americas, the genus has revealed a remarkable chapter in the history of life. Fossils spanning the Oxfordian, Kimmeridgian, Tithonian, and into the early Berriasian stages tell a tale of an enduring predator, one that adapted to different oceans, survived environmental changes, and left behind evidence of its formidable presence for scientists to uncover millions of years later. Each discovery, from the Solnhofen limestone in Germany to the Neuquén Basin in Argentina, has added depth and richness to our understanding of this apex predator, illuminating the incredible diversity and specialization that evolution can produce. Dakosaurus was a true leviathan of the Jurassic and early Cretaceous seas. Its combination of size, strength, and specialized teeth made it a fearsome predator, while its streamlined body and finned tail allowed it to navigate the open oceans with ease. Across Europe and the Americas, Dakosaurus left fossil evidence that continues to captivate scientists and the public alike, revealing a predator that could dominate its environment with both power and precision. Its name, biter lizard, perfectly encapsulates the essence of this marine giant, a creature whose very teeth inspired awe and fear, a master of its prehistoric world, and a reminder of the incredible forms life has taken throughout Earth's history. Through the study of Dakosaurus, scientists have not only uncovered the anatomy of an apex predator, but have also glimpsed the complex ecosystems of the late Jurassic and early Cretaceous oceans. Each fossil provides clues about hunting strategies, ecological roles, and evolutionary adaptations. Fossilized teeth, jaws, and bones allow researchers to reconstruct feeding habits, swimming capabilities, and predator-prey dynamics, offering a window into a world long gone but preserved in stone. The evolutionary journey of Dakosaurus, from its earliest ancestors in the Oxfordian stage to its later species in South America, highlights the adaptability and diversity of marine crocodilomorphs, illustrating how life continually evolves to fill ecological niches. Dakosaurus reminds us of the immense scale and drama of prehistoric oceans. It coexisted with other marine reptiles, fish and cephalopods, all part of a complex web of life where survival depended on skill, speed and power. Its presence at the top of the food chain influenced the behavior and evolution of countless other species, shaping the balance of its marine world. Though it vanished millions of years ago, Dakosaurus endures in the fossil record as a symbol of nature's ingenuity and the raw, primal beauty of an apex predator perfected for life in the ancient seas. Diplocynodon is a fascinating and mysterious genus of extinct crocodiliforms, belonging to the broader group of Eusuchians, which are a kind of ancient crocodilian relatives. Scientists have debated for many years whether these creatures should be classified as early alligatoroids, belonging to the superfamily that includes modern alligators, or whether they might represent a more primitive branch of crocodilian evolution known as stem group crocodilians. What is certain is that Diplocynodon lived in Europe for a very long span of geological time from the Paleocene epoch, which began roughly 66 million years ago, following the catastrophic mass extinction that wiped out the non-avian dinosaurs, to the Middle Miocene epoch, approximately 16 million years ago. This means that for tens of millions of years, Diplocynodon thrived in a variety of European landscapes, adapting to changes in climate, vegetation, and water systems that would have shaped its life and behaviours in remarkable ways. The size of Diplocynodon varied among its different species, and the range of body lengths is quite striking. Some species were relatively modest in size, probably not exceeding 1 metre, which is a little over 3 feet in length. These smaller forms would have been nimble hunters, slipping through freshwater rivers, lakes, and marshes, hunting for fish, amphibians, and perhaps small mammals and birds. Other species were much larger, reaching lengths of about 3 metres, or nearly 10 feet, a size that would have made them formidable predators in their habitats. Such larger Diplocynodon would have possessed a strong muscular body, powerful jaws lined with teeth capable of catching slippery prey, and a tail built for propelling itself swiftly through the water. The differences in size among species suggest a wide diversity in lifestyle and ecological role, with smaller individuals perhaps avoiding direct competition with larger relatives or other crocodiliforms that shared the same environments. Almost all Diplocynodon fossils are found in association with freshwater habitats, indicating that these animals were highly adapted to life in rivers, lakes, ponds, and swamps. Unlike some modern crocodiles, which can sometimes be found in brackish or coastal waters, Diplocynodon seems to have been almost exclusively a freshwater dweller, depending on calm waters for hunting, shelter, and reproduction. Their adaptations to aquatic life were likely extensive, with strong limbs for swimming, a streamlined body, and a head shape suitable for catching prey both at the water's surface and perhaps below it. It is thought that Diplocynodon species were opportunistic predators, meaning that they would have eaten whatever prey was available in their environment, from small fish and amphibians to potentially birds, mammals, and other reptiles that ventured too close to the water. Their diet and hunting strategy would have varied depending on their size, the available prey, and the particular environment they inhabited at a given time. The history of Diplocynodon's discovery and scientific naming is a tale that stretches back nearly 2 centuries. In the 19th century, paleontologists identified several species from Central Europe, beginning with Diplocynodon steineri, named from fossil remains found in the region of Styria in Austria. Another species, D. styriacus, was identified from sites in Austria as well as France. Later, a third species from Austria was named Eniodon ungeri and was originally placed in its own separate genus. However, further research and comparisons of fossil specimens over the decades revealed that the Austrian and French species were actually the same as Eniodon ungeri. Because the name Diplocynodon was introduced earlier than Eniodon, scientific conventions dictated that the species now be referred to as Diplocynodon ungeri. This example of taxonomic reshuffling illustrates how scientific understanding evolves over time as new specimens are discovered and analysed. In addition to the Austrian and French species, researchers have found that other genera once considered separate also belong to Diplocynodon. For instance, Hispanochampsa from Spain, originally described as a distinct genus, was determined in the year 2006 to be synonymous with Diplocynodon. Similarly, Barifracta deponei from Germany was confirmed in the year 2012 to represent the same genus. These findings suggest that Diplocynodon was more widespread than previously thought, spanning many parts of Europe and exhibiting a remarkable diversity of forms adapted to local ecological conditions. Well-preserved specimens of Diplocynodon have been found in some of the most famous fossil sites in Germany, including the Messel Pit and the Geiseltal lignite deposit. These sites, dating back to the Eocene epoch, approximately 50 to 45 million years ago, provide an extraordinary window into the lives of ancient animals. The Messel Pit, a former lake that became a UNESCO World Heritage Site, preserved fossils in such fine detail that scientists can study bones, skin impressions, and even stomach contents of the animals. Similarly, the Geiseltal lignite deposit, a swampy peat bog in central Germany, has yielded numerous fossils that reveal the ecology of Eocene freshwater environments. Many of the articulated Diplocynodon specimens from these sites are found with gastroliths, which are stones swallowed by the animals. Gastroliths are believed to have aided in digestion by grinding up food in the stomach, a behaviour also seen in some modern crocodilians and other reptiles, suggesting that Diplocynodon had similar physiological adaptations. During the Eocene, the Messel Pit was a calm, swampy freshwater lake surrounded by lush vegetation, with floating mats of plants and a warm, humid climate that supported a diverse array of animals, including fish, amphibians, birds, small mammals, and other reptiles. The Geiseltal site, on the other hand, was more of a dense peat bog swamp, with thick vegetation and standing water that would have provided ideal habitats for crocodilians like Diplocynodon. In these freshwater landscapes, Diplocynodon would have hunted, basked on banks or fallen logs, and perhaps interacted with other aquatic or semi-aquatic predators. Its presence in these sites also allows modern scientists to reconstruct ancient food webs, understanding how energy flowed through Eocene ecosystems and the role that these crocodiliforms played in shaping their environments. From an evolutionary perspective, Diplocynodon is considered one of the basal, or earliest, members of the superfamily Alligatoridea, which today includes modern alligators and caimans. Its precise placement within this group has been clarified through the use of advanced analytical techniques that combine multiple lines of evidence. A notable study conducted in 2018 by Lee and Yates applied a method called tip dating, which simultaneously considers morphological features, DNA sequencing from living relatives, and the age of fossil specimens. This integrated approach has provided a more refined understanding of Diplocynodon's evolutionary relationships and has placed it as one of the foundational members of the alligatorid lineage, although debates continue regarding its exact position. More recent research continues to challenge traditional assumptions about Diplocynodon. In the year 2025, Jules D. Walter and colleagues argued that many anatomical features previously thought to be unique to alligatoroids were actually more widespread among other groups. Their analysis suggested that several genera, including Diplocynodon, traditionally viewed as basal alligatoroids, might not even belong to the alligatorid superfamily at all. Instead, these animals could represent derived non-crocodilian Eusuchians, a branch of ancient crocodiliforms that evolved specialized characteristics independently from true crocodilians. This highlights the complexity of interpreting fossil evidence and shows that the evolutionary history of these animals is more intricate than previously appreciated. Investigations into the growth patterns and biology of Diplocynodon species have provided fascinating insights into their life history. For example, osteohistological studies of Diplocynodon hantoniensis, a species known from Europe, suggest that it grew in a manner similar to modern American alligators. This growth pattern was determinate, meaning that the animals reached a maximum size and then largely stopped growing, and it was also seasonally controlled, with periods of faster growth likely corresponding to favourable environmental conditions, such as warm seasons or periods of abundant food. Furthermore, the allometric measurements of D. hantoniensis, particularly the length and circumference of its femur bone, scaled in a pattern comparable to modern American alligators, indicating similar locomotor capabilities and body proportions. These findings provide a glimpse into how Diplocynodon developed and lived, suggesting a combination of slow, steady growth with bursts of activity during times of plentiful resources. Advanced imaging techniques, such as computed tomography, CT scans, have been applied to other species of Diplocynodon, revealing internal structures of the skull and brain. For example, CT scans of Diplocynodon tormis have allowed scientists to reconstruct the snout and portions of the brain, offering clues about sensory capabilities and cognitive functions. The olfactory bulbs responsible for the sense of smell are proportionally similar to those of alligatoroids, although they are smaller than in some true crocodiles, supporting the idea that Diplocynodon had close anatomical ties to alligatoroids. Meanwhile, the optic lobes and overall encephalization quotient, which is a measure of brain size relative to body size, are proportionally smaller than in other medium-sized crocodilians, although some of this difference might be due to incomplete fossil preservation. These observations suggest that Diplocynodon had a brain and sensory system adapted to hunting and surviving in freshwater environments, relying on smell and sight to detect prey and navigate complex aquatic habitats. Diplocynodon's ecological role can also be inferred from the study of fossil sites in Europe, such as the Lutetian deposits of Geiseltal. Analysis of skull shapes and jaw mechanics indicates that Diplocynodon was likely a small generalist carnivore. This means that it probably hunted a variety of prey without specializing in a particular food source, taking advantage of whatever animals were available within its reach. Its hunting behavior would have complemented that of larger crocodiliforms, such as Anatosuchus, which shared the same habitats. By occupying a different size niche and focusing on different prey, Diplocynodon and these larger crocodilians could coexist without direct competition, partitioning resources in a manner that supported multiple predators within the same ecosystem. Stable isotope analysis further enriches our understanding of Diplocynodon's diet. Specimens from the late Oligocene site of Enspel in what is now Germany, were examined for their enamel values, a chemical signature that reflects the types of food an animal consumed during its lifetime. These studies indicate that Diplocynodon primarily fed on aquatic vertebrates, such as fish, amphibians, and possibly small reptiles, aligning with its morphological adaptations for life in freshwater environments. Its feeding strategy would have been opportunistic, allowing it to exploit seasonal variations in prey availability and navigate complex aquatic landscapes with efficiency. Fossil evidence also provides a glimpse into the behavioural and physiological traits of Diplocynodon. The presence of gastroliths in articulated specimens suggests not only a digestive adaptation, but also hints at possible behaviours such as deliberate ingestion of stones to aid buoyancy control, as seen in some modern reptiles. Its body proportions, limb structure, and skull morphology indicate that it was a capable swimmer, able to manoeuvre through dense vegetation, shallow waters, and open lakes with relative ease. Observations from multiple sites, combined with studies of growth patterns, brain structure, and dietary preferences, paint a picture of an animal that was well suited to its environment, both as a predator and as a participant in complex aquatic ecosystems that included fish, amphibians, birds, mammals, and other reptiles. Diplocynodon's fossil record spans multiple countries in Europe, including Germany, Austria, France, and Spain, suggesting that it was highly adaptable and capable of surviving in a variety of climatic and ecological conditions. From the warm, swampy lakes of the Eocene to the more temperate environments of the Oligocene and Miocene, Diplocynodon persisted through significant changes in climate, vegetation, and faunal communities. Its ability to thrive over such a long period highlights not only its ecological flexibility, but also its evolutionary resilience, as it evolved morphological and behavioural adaptations that allowed it to persist, while other crocodiliform lineages went extinct. The study of Diplocynodon continues to provide important insights into the evolutionary history of crocodilians and their relatives. By examining fossil evidence, growth patterns, brain morphology, feeding habits, and ecological interactions, scientists can reconstruct a vivid picture of how this genus lived, hunted, and interacted with its environment. Each new discovery, whether a well-preserved skull, a set of gastroliths, or a CT scan revealing internal cranial anatomy, adds depth to our understanding and allows for more refined reconstructions of its biology. Diplocynodon stands as a remarkable example of an ancient aquatic predator that lived for tens of millions of years, adapting to a dynamic and changing world, and offering modern science a window into the complex ecosystems of prehistoric Europe. Over time, Diplocynodon has captured the interest of paleontologists not only because of its distinctive evolutionary position, but also because of its wide geographic distribution and long temporal range. From the first descriptions in the 19th century to the latest analyses using cutting-edge technology, this genus exemplifies the way scientific knowledge evolves. Its fossils reveal stories about life in freshwater environments long before humans existed, about the interactions between predators and prey, and about the intricate balance of prehistoric ecosystems. The specimens from Germany, Austria, France, and Spain, preserved in incredible detail, allow us to study the minutiae of anatomy, physiology, and behaviour, and to compare them with modern relatives such as alligators, crocodiles, and caimans. Scientific studies of Diplocynodon also illustrate the ongoing debates and revisions in paleontology. Early classifications placed many species in separate genera, or assumed close relationships to modern crocodilians, but new analyses using morphology, molecular data, and stratigraphy continue to refine our understanding. Research by Lee and Yates in 2018, and later by Walter and colleagues in 2025, demonstrate that our understanding of evolutionary relationships is constantly shifting as new evidence emerges. The genus Diplocynodon serves as a case study in how science progresses, integrating fossils, growth studies, anatomical reconstructions, and isotopic analyses to build a more complete picture of an extinct animal. The internal structure of Diplocynodon's skull and brain also sheds light on its sensory and cognitive abilities. The relatively well-developed olfactory bulb suggests a reliance on smell for detecting prey and navigating its environment, similar to modern alligators. However, the optic lobes and brain size relative to body mass indicate that it may not have relied as heavily on vision or complex processing as some crocodiles do. These anatomical insights help reconstruct not only the behaviour, but also the ecological niche of Diplocynodon, showing it as a medium-sized, versatile predator that could coexist with larger crocodilians, fish-eating birds, and other aquatic animals in freshwater lakes, swamps, and rivers. Dietary analysis from chemical signatures in tooth enamel indicates a preference for aquatic vertebrates, which fits well with the freshwater habitats from which most specimens are recovered. In combination with studies of jaw mechanics and skull morphology, these findings suggest that Diplocynodon was not a specialized predator but rather a generalist, capable of taking advantage of a wide range of prey types. Its smaller size compared to other crocodilians in the same ecosystems would have allowed it to exploit niches that were unavailable to larger predators, reducing competition and enhancing its ability to survive over long periods. The remarkable preservation of some specimens, especially those from Messelpit and Geiseltal, provides unparalleled insight into the biology of Diplocynodon. Gastroliths found within the stomach region, for example, not only illustrate feeding and digestive behaviour, but also hint at potential adaptations for buoyancy or even behavioural habits, such as swallowing stones deliberately. These discoveries, combined with osteohistological studies showing seasonal growth patterns, indicate that Diplocynodon lived in environments with seasonal changes in temperature and resource availability, adjusting its growth and activity levels in response to these conditions. The fossil record of Diplocynodon presents a vivid picture of an ancient genus that thrived in European freshwater ecosystems for tens of millions of years. Its wide range of sizes, from small, agile hunters to larger, more powerful predators, combined with anatomical, physiological, and chemical evidence, illustrates a genus that was versatile, adaptable, and highly integrated into the food webs of its time. Each fossil specimen, each CT scan, and each chemical analysis contributes to a growing understanding of the life and times of Diplocynodon, allowing scientists to reconstruct not only the anatomy of this ancient crocodilian relative, but also the dynamic ecosystems in which it lived. Armadillosuchus is an extinct type of crocodilomorph, belonging to a family known as Sphagosaurids. This ancient reptile first came to scientific attention in February of 2009, when fossils were described from the Adamantina Formation, a geological layer found in the Bauru Basin of Brazil. These rocks date from the late Campanian to the early Maastrichtian ages of the Cretaceous period, which is roughly 70 million years ago. Among its relatives, Armadillosuchus stood out as one of the larger and more powerfully built Sphagosaurids, reaching an estimated total length of about 2 meters, or 6.5 feet. Like other members of its family, Armadillosuchus had what is called heterodont dentition, meaning its teeth were not all the same shape. This unique dental arrangement likely allowed it to chew its food, which is unusual for crocodilomorphs. Scientists believe that Armadillosuchus was an omnivore, eating a mixture of small animals, invertebrates, and plants, and it may have scavenged meat when the opportunity arose. Its strong and well-developed forelimbs suggest it could dig, possibly creating burrows to escape the heat or cold and to regulate its body temperature in the harsh environment of prehistoric Brazil. One of the most striking features of Armadillosuchus was its body armour. Fossil evidence shows a rigid shield of hexagonal bony plates called osteoderms just behind its head, followed by a series of flexible bands reminiscent of modern armadillos. These armoured bands likely contributed to the genus's name. Interestingly, while this armour is clearly visible in fossils, some research suggests that in life it may have been embedded deep into the skin, making it less obvious than it appears in the fossilised remains. Currently, the genus Armadillosuchus includes only a single name species, Armadillosuchus arudai, making it monotypic. However, fragmentary fossils discovered in the Adamantina Formation hint at the possibility that other species may have existed. The first fossils of Armadillosuchus were uncovered in rocks of the Adamantina Formation in General Salgado County in Brazil. At first, these rock layers were thought to date from the Turonian to Santonian ages, but later research revised their age to the younger Campanian to Maastrichtian. The holotype, or primary reference specimen for the species, and is a remarkably well-preserved partial skeleton. It includes the complete skull, neck, cervical osteoderms, the front portion of the torso, and nearly a complete left forelimb. Alongside it, two paleontologists, Tiago S. Marinho and Ismaris Carvalho, described a second, less complete fossil, which they designated as the paratype of Armadillosuchus. This specimen preserves only parts of the upper and lower jaws. Although less complete, the paratype could be confidently assigned to the genus thanks to the distinctive teeth it shared with the holotype. Later discoveries added more fossil material, totaling 165 skeletal elements, though many of these were fragments and poorly preserved because parts of the fossils had been exposed to erosion. While these additional remains show clear similarities to Armadillosuchus, there are notable differences as well. Because of these differences, the specimen is referred to only as Armadillosuchus spe, suggesting it might represent a separate species within the genus. The name Armadillosuchus reflects its most obvious characteristic. The first part, armadillo, comes from Spanish, chosen because its bony armour resembles the protective shells of modern armadillos. The second part, suchus, is derived from the ancient Greek word for crocodile and is commonly used in naming fossil crocodilomorphs. The species name, Arudae, honours João Tadeu Arruda for his many contributions to the paleontology of the region. Even though the fossil of Armadillosuchus is not entirely complete, its protective armour has helped preserve much of the skeleton in remarkable detail. The skull is robust and slightly flattened, maintaining the typical overall shape seen in Notosuchians. The snout is relatively longer and broader than in close relatives like Deinosuchus and Sarcosuchus, yet it remains short by general crocodile standards. The teeth of Armadillosuchus are highly varied. Unlike the uniform teeth of most crocodiliforms, these include curved, canine-like teeth at the front, protruding incisors, and conical malariform teeth with shearing edges toward the back. Each side of the upper front jaw, the premaxilla, contains only 2 to 3 teeth, with the second tooth of each side being a large caniniform. Further back in the upper jaw, the teeth are asymmetrical, with the outer side smooth and the inner side lined with small tubercles. The lower jaw is narrower than the upper jaw, with the front teeth angled forward, similar to those of Deinosuchus and Purussaurus. One of the lower teeth is flattened and has a front-facing keel, while the teeth further back resemble the rear upper teeth, though the tubercle-lined keel faces outward rather than inward. The ribs of Armadillosuchus show pachyostosis, meaning they are thickened, a feature that may have helped support its heavy body. Its limbs were long for a crocodilomorph but relatively short compared to other sphagosaurids, with a robust humerus measuring about half its total length. The shoulder blade is stout, roughly equal in height and width, reflecting a strong muscular forelimb capable of digging. Within sphagosaurids, Armadillosuchus is considered one of the larger species. Its skull measures around 300 millimeters, or about 12 inches, nearly twice the size of smaller relatives like Yacararani and Deinosuchus. Its total body length may have reached about 2 meters, or 6 feet and 7 inches. Like other crocodilomorphs, Armadillosuchus was protected by prominent bony plates, or osteoderms. Behind the skull, these plates fuse into a rigid hexagonal shield that protected the neck. This cervical or nuchal shield, decorated with horizontal ridges, could move independently from the head, allowing flexibility while still offering protection. Behind this shield were 7 mobile bands of thoracic armour, resembling those of modern armadillos. These overlapping rectangular osteoderms were ornamented with circular pits, similar to other Neosuchians. The first 5 bands each had 4 parallel plates, while the 6th and 7th bands had only 2. Beyond these, it is suggested that the armour may have simplified into a double row, resembling that of modern crocodiles. Fossilised remains of the tail show osteoderms ranging from rectangular to somewhat triangular, generally wider than long, and a variety of smaller accessory plates were also present. In life, Armadillosuchus must have been a striking creature. A heavily armoured, broad-skulled and versatile omnivore with strong digging limbs, a flexible yet protective body shield, and teeth specialised for handling a wide range of foods. Its fossils continue to reveal new details, hinting at the possibility of additional species waiting to be discovered in the ancient landscapes of Brazil. Armadillosuchus, together with its relative Sarcosuchus, stands out as one of the most heavily armoured members of the Notosuchian crocodilomorphs. However, a study published in the year 2020 has revealed that the armour of Armadillosuchus may not have been visible in life in the same obvious way that the scales and osteoderms appear in today's crocodiles. The research focused on a special structure called Sharpie's fibres, which are made of collagen and serve to attach the bony plates of the osteoderms to the underlying layer of the skin, known as the stratum compactum. In modern crocodiles, these fibres mainly help to keep the base of the osteoderms firmly connected to the skin. But in Armadillosuchus and many other Notosuchians, the fibers also run perpendicular to the outer surface of the bony plates. A similar condition is seen in today's leatherback turtles and softshell turtles, which led the researchers to suggest that the osteoderms of Armadillosuchus were deeply embedded in thick skin, covered with a leathery layer. This arrangement may have given the animal greater flexibility while moving. Recent studies of evolutionary relationships consistently show that Armadillosuchus was a more derived or advanced member of the Sphagosauridae family. This family of Notosuchians was native to South America and is known for having different types of teeth adapted to a variety of diets, a condition called heterodonty. Within the Sphagosaurids, scientists have noticed a general division between smaller, short-snouted, lighter-built species like Deinosuchus and much larger, heavily armoured and robust forms, which include Armadillosuchus. Among these larger Sphagosaurids, Armadillosuchus appears to be most closely related to Carnufex. A phylogenetic analysis carried out by Kuhnher and colleagues in the year 2020, following the discovery of fossil remains of an unnamed species of Armadillosuchus, revealed a clear evolutionary link between Armadillosuchus arudi and this second unnamed species. Yet, the analysis also placed both species alongside Carnufex in a polytomy, indicating some uncertainty about the precise branching order. Investigations into the resting metabolic rate and estimates of red blood cell size indicate that Armadillosuchus, like modern crocodiles, was likely ectothermic, meaning it relied on external heat sources to regulate its body temperature. Despite this, Armadillosuchus and other terrestrial Notosuchians may have managed their body heat in a way similar to today's monitor lizards. They likely basked in the sun to warm themselves and preferred sunlit areas while foraging. When temperatures became too high, they could retreat into burrows for cooling. The osteoderms may have played an additional role in thermoregulation, helping to absorb and store heat for long periods, allowing the animal to remain active even without direct sunlight. The teeth of Armadillosuchus provide important clues about its lifestyle and diet. Their shape and arrangement suggest that the animal had very powerful scissor-like jaws, where patterns on the teeth show that Armadillosuchus moved its jaws back and forth while chewing, similar to the motion seen in the related genus Sphagosaurus. However, the exact way the teeth fit together differs from Sphagosaurus. In Armadillosuchus, the fifth tooth of the lower jaw sits just before the third tooth of the upper jaw. This unique arrangement may have been an adaptation for foraging underground. Supporting this idea is the animal's robust anatomy: a strong shoulder girdle, long claws on its forelimbs, and a sturdy neck. Its forelimbs may have been used for digging burrows or foraging in the soil, consistent with the thermoregulatory habits described earlier. One hypothesis about the diet of Armadillosuchus suggests that it was an omnivore, feeding on a mix of plants and animals such as mollusks, insects, and other arthropods, roots, and pine seeds. Even though no mollusk shells have been found directly near its fossils, the Adamantina Formation, where these remains were discovered, had rivers and lakes and preserves, the remains of bivalves in other nearby areas, which supports this dietary possibility. It is also likely that Armadillosuchus occasionally scavenged, feeding on dried carcasses, which could explain some of the tooth wear observed in the fossils. In addition to the tubercles on the keels of the molar-like teeth and the grinding motion of the jaws, this animal may have used small stones, known as gastroliths, to help grind tough food. A more detailed study of the teeth, published in 2019, used a method called orientation patch count rotated, originally developed to measure the complexity of rodent teeth. This technique has shown a strong connection between the shape of teeth and diet across many groups of animals, including reptiles. The results for Armadillosuchus revealed tooth complexity values that fall between those of primarily carnivorous reptiles, like Bovirusuchus and Notosuchus, and gyrophagus reptiles, like Allodaposuchus and Brachychampsa, which specialize in crushing hard food. This suggests that Armadillosuchus had a diet that could include insects, or a mix of plant and animal matter, but given its large size, an omnivorous diet seems more likely. The large, stout body of Armadillosuchus, together with its underlying bony armour, would have made it well protected against predators. Its extensive armour has been compared not only to modern armadillos, but also to the heavy osteoderm seen in ankylosaurid dinosaurs. This combination of size and protection unites large-bodied Sphagosaurids like Armadillosuchus and Carnufex, setting them apart from the smaller and more lightly built early Sphagosaurids such as Purussaurus. Aegisuchus is an extinct genus of enormous flat-headed crocodiliform reptiles belonging to the family Egyptosuchidae. Only a single species is known, making it monospecific. Fossils of this strange and fascinating creature were discovered in the Kem Formation, located in the southeastern part of Morocco. This geological formation is dated to the Cenomanian age of the late Cretaceous period, approximately 100 million years ago. The type species, named Aegisuchus whitmeri, was officially described in the year 2012 by the paleontologists Casey Holliday and Nicholas Gardner. They affectionately nicknamed it shield croc, because the top of its skull resembled a broad shield-like shape. The species is known solely from a partial skull, including the brain case and the roof of the skull, catalogued under the number ROM 54530. The skull of Aegisuchus exhibits a number of unique features that distinguish it from all other crocodiliforms. At the very centre of the skull table is a raised, circular, rough-surfaced area called a boss, located on the parietal bone. On each side of this central boss are holes known as dorsotemporal fenestrae, while the surrounding bone remains relatively smooth. In the temporal region of the skull, the quadrate bone bears a rectangular projection called the adductor tubercle, which provided a strong attachment point for the muscles that closed the jaw. At the front of the skull, projections called capitate processes extend outward from the laterosphenoid bones, a feature also seen in modern gharials, though it evolved independently in Aegisuchus. The front surface also has two more dorsotemporal fenestrae that pass completely through the skull and open at the skull table. A bony ridge, or torus, forms the lateral edge of each hole. The back of the skull is broad, with large projections on the exoccipital bones, which would have anchored the massive epaxial muscles along the top of the neck. Remarkably, the brain case of Aegisuchus is unusually large, with a volume of 40 cubic centimetres, making it bigger than that of any other known crocodiliform. Based on comparisons between the brain case and total skull length in other crocodilians, researchers initially estimated that the total skull length of Aegisuchus ranged between 2.08 to 2.86 metres, or approximately 6 feet 8 inches to 9 feet 4 inches. When using ratios of skull to body length, some estimates suggested a total body length as long as 15 to 21 metres, which is 49 to 69 feet, if it had proportions similar to long-snouted gharials. Alternatively, if it had proportions like short-snouted crocodiles, the length could have reached 16 to 22 metres, or 52 to 72 feet. These extreme estimates, however, have been questioned, and more cautious analyses suggest that Aegisuchus probably did not exceed 15 metres, or 49 feet in total length. Later recalculations based on regression equations suggested an actual skull length of only 62 to 90 centimetres, or roughly 2 feet to 2 feet 11 inches, implying a total body length closer to 3.9 metres, or 13 feet. One of the most striking features of Aegisuchus is the circular, roughened boss on the skull table. Like in modern crocodilians, this textured region was likely covered with thick, tough skin that closely adhered to the bone. Surrounding the central boss is a smooth area that displays deep, parallel channels for blood vessels, indicating that this region may have supported thick, complex skin tissue. No other crocodilian shows such pronounced vascularization, suggesting that this feature might have been unique to Aegisuchus. Because the blood vessel channels extend toward the brain case, the tissue may have helped regulate temperature by warming blood travelling to the brain and eyes. Additionally, the boss may have played a role in mating displays, possibly functioning as a striking eye spot. Modern crocodilians often raise their heads above the water as part of courtship and social signalling, and as a close relative, Aegisuchus likely engaged in similar behaviours. The flattened shape of its skull also provides insight into the lifestyle of Aegisuchus. It was likely an ambush predator, lying in wait near the water's surface to strike unsuspecting prey. While only the back portion of the skull is known, features can be inferred from its close relative, Egyptosuchus. Aegisuchus probably had upward-facing eyes, with no raised ridges surrounding the eye sockets. A bony strut called the postorbital bar, which is usually vertically oriented in most crocodilians, would have been nearly flat. The flattened skull required significant changes in jaw musculature. The adductor muscles, responsible for closing the jaw, shifted to a more vertical orientation. Muscles like the adductor mandibulae externus medialis, which are relatively weak in most crocodilians, became enlarged and crucial for closing the jaws. The broad back of the skull provided ample attachment for the splenius capitis muscles in the neck, essential for lifting the head and opening the mouth. With such a long, flattened snout, Aegisuchus would have needed these large neck muscles to effectively raise its head. A depressed area at the lower rear of the skull also indicates large jaw-closing muscles, further aiding in opening the mouth. Interestingly, a similar mechanism is observed in the late Triassic amphibian Gerothorax. Furthermore, Aegisuchus had a highly flexible joint between its skull and spine, allowing it to raise its head much higher than most modern crocodilians. During the late Cretaceous period, the northern regions of what we now call Africa were not the arid deserts that many imagine today. Instead, this area was a warm, humid and lush landscape, teeming with life and crisscrossed by rivers, lakes and wetlands. It was a world defined by the presence of the Tethys Ocean, a great seaway that stretched like a watery ribbon between the massive southern continents that geologists call Gondwana and the northern land masses collectively known as Laurasia. The Tethys Ocean, a crucial feature of this ancient world, created coastlines, deltas and estuaries, shaping environments where water and land intertwined to create thriving ecosystems that supported an astonishing variety of creatures, from tiny fish to the gigantic dinosaurs that roamed the earth. Within this vibrant and watery realm, the Kem beds of southeastern Morocco were slowly forming. These beds, today studied as a treasure trove for paleontologists, are layers of sediment that were deposited within what was once a sprawling freshwater delta system. Imagine a network of rivers spreading out into a floodplain, their waters rich with sediment and nutrients, forming channels, lagoons and muddy banks where life flourished. It was within this setting, a world of intertwining water and land, that a remarkable creature known as Aegisuchus lived. This enormous, now extinct crocodiliform, part of the family Egyptosuchidae, was among the apex predators of its environment, a hidden giant in the shallow waters and riverbanks of northern Africa, its life intertwined with the rhythms of the freshwater delta it called home. Aegisuchus, which has been preserved in the fossil record from skull material discovered in the Kem beds, had a striking and unusual appearance, even by the standards of crocodilian evolution. Its most distinctive feature was its extremely flattened and broad skull, which likely gave it the shape of a living armoured shield. This strange and almost otherworldly head form is a clue to how the animal hunted and survived. Modern crocodilians, like the Nile crocodile or the alligator, use ambush tactics to capture prey, waiting quietly, almost invisibly, for animals to come within striking distance before lunging with explosive speed. It is thought that Aegisuchus, with its flattened head and long body, used a similar strategy. It may have lain partially submerged in the muddy waters of the delta, its eyes and nostrils barely visible above the surface, a silent shadow waiting for unsuspecting prey to wander too close. Its ambush technique was likely enhanced by its wide skull, which could cover a larger area and allow for a sudden and powerful bite. The diet of Aegisuchus would have been diverse and opportunistic, reflecting the abundance of life within the delta system. Fossils found in the same geological layers reveal that the Kem beds were home to an array of fishes, including coelacanths, ancient lungfish, and beachirs, all of which were slow-moving and would have been ideal prey for a patient ambush predator. However, Aegisuchus was not restricted to hunting only aquatic creatures. Its large size and strength meant it could have preyed upon smaller land vertebrates venturing too close to the water's edge. This could have included reptiles like lizards and snakes, or even the occasional hatchling dinosaur wandering near the rivers. The diversity of potential prey reflects a key trait of many successful predators: flexibility. By feeding on both aquatic and terrestrial animals, Aegisuchus would have maintained an advantage in an environment where resources could fluctuate with the seasons and river levels. Despite its position near the top of the food chain, Aegisuchus was not without danger. The late Cretaceous delta was home to other formidable predators, some of which could have posed a threat even to such a large crocodiliform. One such predator was Spinosaurus, the colossal semi-aquatic dinosaur that could reach lengths of over 15 meters, its long crocodile-like snout bristling with conical teeth. Spinosaurus is known to have inhabited the same regions as Aegisuchus, and while interactions between the two are speculative, it is possible that juvenile Aegisuchus or weakened individuals could have fallen prey to this enormous predator. This dynamic paints a picture of a dangerous and competitive ecosystem, where even the largest predators had to remain vigilant and cunning to survive. the significance of Aegisuchus extends beyond its role as a predator in the Chem-Chem delta. Its existence provides critical insights into the evolution of crocodilians during the late Cretaceous, a period of dramatic geological and biological change. The world at this time was far from static. Land masses were drifting apart due to the forces of plate tectonics. Europe and Asia were gradually moving away from Africa, expanding the waters of the Tethys Ocean and fragmenting ecosystems that had once been connected. North America, meanwhile, continued to separate from the rest of Laurasia, allowing the Atlantic Ocean to widen and creating new coastlines and seaways. These movements reshaped habitats, influencing which species could survive, adapt, and disperse across continents. Crocodiliforms, the broader group to which Aegisuchus belonged, were undergoing a period of significant diversification. Early crocodilians, including forms like Borreliosuchus, were present in North America, leading many researchers to hypothesize that crocodilia, the group that includes all modern crocodiles, alligators, and gharials, may have originated on that continent. However, the discovery of Egyptosuchids, such as Aegisuchus in northern Africa, challenges this view and suggests a more complex story of crocodilian evolution. Rather than being confined to one area, early crocodiliforms appear to have flourished around the Tethys Ocean, taking advantage of the rich and varied delta and coastal environments of northern Africa. Aegisuchus and its relatives, the Egyptosuchids, were highly specialized crocodiliforms. Unlike the more generalized forms found elsewhere, these animals exhibited adaptations that allowed them to thrive in very specific ecological niches. Their flattened heads, for instance, may have been suited for stealth hunting in wide, shallow rivers, while their strong jaws and teeth could capture a broad range of prey. The Egyptosuchids demonstrate that crocodilian evolution was not only about survival, but also about experimentation with body plans and hunting strategies. These animals represent a branch of the crocodilian family tree that was highly endemic, meaning they were largely restricted to particular regions and environments. Their evolution was closely tied to the waterways and floodplains of northern Africa, making them an integral part of the story of life around the Tethys Ocean. The ecosystem of the Chem-Chem beds was incredibly diverse. Alongside Aegisuchus, paleontologists have discovered remains of numerous other animals that paint a vivid picture of life in this ancient delta. Stomatosuchids, another family of crocodilian predators, shared similar habitats and likely competed for some of the same resources. The rivers and floodplains were populated by turtles, whose hard shells provided some protection, but also made them appealing targets for a strong predator. Snakes and lizards, including large varanids, moved among the vegetation and riverbanks, feeding on smaller animals while remaining alert to the dangers posed by crocodiliforms. Pterosaurs, the flying reptiles of the Mesozoic, would have skimmed above the water or perched along the banks, hunting insects or small vertebrates while avoiding predation. Sauropods, the massive long-necked herbivorous dinosaurs, roamed the floodplains, while theropod dinosaurs ranging from mid-sized hunters to enormous apex predators navigated the same landscapes, creating a complex web of interactions among predators and prey. The rivers themselves were home to an astonishing array of fish species. Coelacanths, sometimes described as living fossils because of their ancient lineage, were slow-moving and plump, perfect for a patient ambush predator. Lungfish, which can survive in oxygen-poor waters, and bashirs, elongated and armoured, added to the richness of the aquatic environment. Each of these species contributed to the balance of life in the delta, providing food for predators like Aegisuchus, while also playing roles in the cycling of nutrients and the health of the aquatic system. The presence of such a wide range of fishes indicates that the freshwater systems of the Chem-Chem beds were both extensive and productive, supporting complex food chains that included both small and massive creatures. The climate of the late Cretaceous in northern Africa, being warm and humid, would have further shaped the behaviour and evolution of Aegisuchus. In such an environment, water levels could fluctuate seasonally, with periods of flooding and drought affecting the availability of prey and suitable habitats. Aegisuchus, with its ambush style of hunting, would have been well adapted to these changes. During times of high water, it could have taken advantage of flooded areas to ambush fish and other aquatic prey. During drier periods, when rivers and lakes receded, it might have ventured closer to land, targeting reptiles and smaller vertebrates forced into smaller pools of water. This flexibility would have been crucial for survival, in an environment where conditions could change rapidly, demonstrating the adaptability that characterizes successful predators both in the past and today. The study of Aegisuchus also provides a glimpse into the broader patterns of crocodiliform evolution during the late Cretaceous. As continents drifted and oceans widened, populations of crocodilians became increasingly isolated, allowing for the development of unique and highly specialized forms. Northern Africa, situated along the edges of the Tethys Ocean, became a hotspot for such evolutionary experiments. The Egyptosuchids represent just one example of this process, a lineage that evolved remarkable adaptations for ambush hunting in freshwater environments, becoming distinct from other crocodilian forms found in Europe, Asia, and North America. The diversification of these animals highlights how geography, climate, and ecological opportunity interact to shape the evolution of species over millions of years. In addition to its ecological and evolutionary significance, Aegisuchus captures the imagination because of its sheer size and strange appearance. While exact measurements are difficult to determine from the limited fossils, it is clear that this crocodiliform was among the larger predators of its time. Its broad, flattened skull, combined with its long and muscular body, suggests a creature capable of delivering a sudden, devastating bite. Fossil evidence of other predators and prey in the chem beds allows scientists to reconstruct possible interactions and behavior. For instance, Aegisuchus may have lurked beneath the muddy waters, while lungfish and coelacanths swam nearby, striking with lightning speed. On land, it may have ambushed small reptiles that came to drink, while remaining wary of the enormous theropods like Spinosaurus that shared the delta. Aegisuchus, along with its relatives in the Egyptosuchidae, contributes to a broader understanding of how crocodilian diversity expanded during the late Cretaceous. As continents broke apart and new habitats emerged, these animals took advantage of ecological niches that may have been unavailable in other regions. Their specialized adaptations show that the evolutionary story of crocodilians is not one of simple continuity, but of experimentation and diversification, with some lineages exploring new forms and behaviors, while others followed more generalized paths. The evidence from northern Africa suggests that the Tethys Ocean, rather than North America, may have been a central stage for the evolution of some of these unique crocodiliforms, challenging previous ideas about the origins and spread of early crocodilians. The world of the chem beds was thus a dynamic and interconnected ecosystem, with rivers, floodplains, and wetlands providing the setting for a rich tapestry of life. Aegisuchus occupied a special place within this system, a predator both formidable and specialized, adapted to a life of ambush in the shallow waters and muddy banks of northern Africa. The interactions between Aegisuchus and other species, from fish and turtles to giant theropods, reflect a complex food web in which survival required not only strength and size but also patience, cunning, and adaptability. The presence of this crocodiliform, alongside other Egyptosuchids and a diverse array of coexisting species, underscores the intricate and fascinating nature of late Cretaceous ecosystems along the Tethys Ocean, a world both alien and compelling whose remnants continue to be uncovered in the fossil record of Morocco. Aegisuchus and the chem beds together provide a vivid illustration of the interplay between environment, evolution, and ecology. In a landscape shaped by rivers, deltas, and the distant waters of the Tethys, species adapted to their surroundings in remarkable ways, producing forms and behaviors that would vanish with the end of the Cretaceous, but leave behind tantalizing clues in the sediment and bones. Each fossil discovery adds a piece to the puzzle, revealing not only the anatomy of the animals themselves, but also their relationships with other species, their habitats, and the broader forces of plate tectonics and climate that shaped the world in which they lived. The study of Aegisuchus illuminates a moment in deep time when crocodilians were experimenting with new forms, when deltas teemed with fish, turtles, and reptiles, and when northern Africa was a center of evolutionary innovation, a landscape as alive and dynamic as any modern wetland or river delta. By understanding Aegisuchus, scientists gain insight into how ecosystems functioned in the late Cretaceous, how predators and prey interacted, and how geography and climate influenced evolutionary paths. The chem beds continue to yield remarkable fossils, allowing researchers to reconstruct a world long gone, where the waters of the delta were filled with coelacanths and lungfish, where pterosaurs soared overhead, and where immense crocodilians like Aegisuchus waited silently beneath the surface, their eyes and nostrils barely visible, ready to strike in the timeless dance of predator and prey. These discoveries not only inform scientific understanding, but also capture the imagination, offering glimpses of a prehistoric world that, while very different from our own, shares with us the same fundamental principles of life: survival, adaptation, and the relentless drive of evolution across millions of years. Champsosaurus was an ancient reptile that looked a lot like a crocodile, but belonged to a distinct group called the Corystoderes. It lived during the later part of the Cretaceous period and continued into the early Paleogene period, roaming across what is now North America and parts of Europe, roughly from the time known as the Campanian Age up until the Paleocene epoch. Its name, Champsosaurus, has an interesting origin. It is thought to come from the word champsai, recorded in an ancient Greek text as an Egyptian word for crocodiles, and sauros, the Greek word for lizard. Its body shape resembled that of modern gharials, with a long, narrow and elongated snout perfectly suited for catching fish. Champsosaurus lived in freshwater rivers and lakes, where it likely hunted fish in much the same way gharials do today. Champsosaurus holds a special place in paleontology because it was the very first member of the Choristodere group to be scientifically described. The genus was named in the year 1876 by the famous American paleontologist Edward Drinker Cope. Cope based his description on isolated vertebrae discovered in rocks of the late Cretaceous Judith River Formation, along the banks of the Judith River in Fergus County in the state of Montana. Although Cope had initially described another species called Champsosaurus profundus, he chose Champsosaurus annectens as the type species because the specimen included a larger number of vertebrae that he believed were representative. These vertebrae, 9 individual vertebral centra, though sadly 2 of these original bones have since been lost. Over the following years, from 1876 to 1882, Cope described several additional species of Champsosaurus, also using isolated vertebrae as the primary evidence. It was not until 1905 that paleontologist Barnum Brown described the first nearly complete remains of Champsosaurus. Brown carefully examined the fossils and realized that some of the species Cope had named, such as Champsosaurus vaccinsulensis, were actually not Champsosaurus at all, but rather indeterminate remains of plesiosaurs. Brown also noted that the vertebrae Cope used to define his species were highly worn and eroded, and the features along the spine varied so much that they could not reliably distinguish species, even the type species C. annectens. This idea, that C. annectens could not be confidently identified, was later supported by the Canadian paleontologist William Parkes in 1933. Barnum Brown went on to name 2 well-established species of Champsosaurus in 1905. The first, Champsosaurus ambulator, was identified from specimen AMNH 983, a fragmentary skeleton with part of a skull, discovered in the Hell Creek Formation in Montana. The second, Champsosaurus laramiensis, came from specimen AMNH 982, a nearly complete skeleton with a skull, also from the Hell Creek Formation. William Parkes contributed further to the list of species, naming Champsosaurus albertensis in 1927 based on a partial skeleton missing the skull, found in the Horseshoe Canyon Formation of Alberta, Canada. Later, in 1933, Parkes described Champsosaurus natata, based on an incomplete skeleton with a fragmentary skull, from the Belly River group near the Red Deer River in Alberta. Across the Atlantic, in Belgium, paleontologist Denise Sigougnot-Russell named a European species, Champsosaurus dolloi, from fossils found in the Paleocene in the year 1979. In North Dakota, Bruce Erickson named Champsosaurus gigas in 1972, using a partial skeleton and skull from the Sentinel Butte Formation in Golden Valley County. He later described Champsosaurus tenuis in 1980, from a partial skeleton and skull found in the Bullion Creek Formation of the same state. In 1998, K.Q. Gao and Richard Carr Fox published a detailed study that described Champsosaurus lindoi, based on specimen UALVP 931, a nearly complete skeleton with skull and jaws from the Dinosaur Park Formation in Alberta. Their work also reviewed and redefined most of the known species of Champsosaurus, with the exception of C. ambulator and C. laramiensis. Fossils of Champsosaurus have been found across many parts of North America, including the modern regions of Alberta, Saskatchewan, Montana, New Mexico, Texas, Colorado, and Wyoming, as well as in Europe, particularly in Belgium and France. These fossils range in age from the Upper Cretaceous all the way to the Late Paleocene. Some remains that may belong to Champsosaurus have even been tentatively found in the high Arctic of Canada, dating back to the Coniacian to Turonian ages, a time when the Earth experienced extremely warm climates. In total, 16 species of Champsosaurus have been named over the years, but only 7 are currently considered valid. The original type species, Champsosaurus annectens, is now regarded as dubious, and the European species C. dolloi was considered by Gow and Fox in 1998 to be too incomplete to justify a separate species. Most Champsosaurus species were moderate in size, growing to around 1.5 meters, about 5 feet in length. However, the larger species, Champsosaurus gigas, could reach impressive lengths of 3 to 3.5 meters, or roughly 10 to 12 feet, making it one of the most formidable freshwater predators of its time. The skull was flattened from top to bottom, giving it a broad, low profile, while the temporal arches, the bony structures running along the sides of the skull, spread outwards and towards the back. This unique arrangement gives the skull a striking heart-shaped appearance when viewed from above, a feature that no doubt played a role in its powerful bite. Its snout was extraordinarily long and narrow, resembling the delicate, elongated jaws of a modern gharial. This snout made up roughly half of the total skull length, and was at least 4 times longer than it was wide, culminating in nostrils that opened at the very tip. Meanwhile, the ear openings were positioned on the underside of the skull, hidden from view in most illustrations or fossil reconstructions. The body of Champsosaurus reflected its aquatic lifestyle, appearing flat and streamlined, designed to glide smoothly through water. Its belly housed heavy gastralia, or rib-like bones, which would have provided additional support and protection. Compared to other members of the Choristidae family, Champsosaurus had several highly distinctive features in its skull bones. The lacrimal bone, typically found near the eyes, was reduced to a small triangle, while the postorbital bone did not participate in forming the eye socket. Interestingly, the premaxilla and vomer bones did not touch each other, and an internarial bone was present, a feature not common in all reptiles. Its choanae, the internal openings of the nasal cavity, were shifted far back to match the elongated shape of the vomer. The interpterygoid vacuity, a small hole between certain bones of the palate, was compact, fully enclosed by the pterygoid bones and located near the rear edge of the suborbital fenestra, which itself was shortened and kidney-shaped. The pterygoid and parasphenoid bones were fused together, while the joint connecting the skull and lower jaw lay in front of the occipital condyles at the back of the skull. A unique neomorphic bone largely bordered the posttemporal fenestra. The paraccipital process curved sharply downward, and the basal tubera of the psisphenoid extended backward and downward like wings. The lower jaw was equally impressive. The mandibular symphysis, or the connection between the two halves of the lower jaw, stretched over half the length of the tooth row, with the splenial bone playing a significant role in reinforcing this structure. These features collectively made Champsosaurus a creature with a skull built for precision, strength, and specialized hunting. The brain case of Champsosaurus revealed more about its sensory capabilities. At the front, the brain case was poorly ossified, meaning the bones were relatively soft or incomplete, but at the rear it was well developed, much like other diapsid reptiles. The cranial endocast, the space within the skull that housed the brain, showed proportions similar to early archosauromorph reptiles, being narrow both top to bottom and side to side. The pineal body, often associated with regulating light cycles, was enlarged, as were the olfactory bulbs, which suggested that Champsosaurus likely had a keen sense of smell. Its optic lobes and flocculi were small, indicating that its vision was perhaps only average by reptilian standards. The nasal passages were spacious, further supporting its olfactory abilities, although they lacked bony turbinates, structures that in modern animals help warm and filter air. The semicircular canals of the inner ear resembled those of other aquatic reptiles, hinting at its swimming skills. Moreover, an expanded sacculus in the ear implied heightened sensitivity to low-frequency sounds and vibrations in water. Yet, the absence of an otic notch, and likely no tympanum, suggested that Champsosaurus was not well suited to detecting airborne sounds, and may have relied primarily on underwater auditory cues. Champsosaurus's teeth were another marvel of adaptation. Like other Neochoristidae, its teeth had striated enamel on the crowns with additional enfolding at the base, creating both strength and grip. The front teeth were sharp and slender, perfect for piercing slippery prey like fish. while the rear teeth were broader and more robust. Unique among reptiles, Champsosaurus had palatal teeth on the bones of the roof of its mouth, arranged in longitudinal rows on the pterygoid, palatine, and vomer bones, with a smaller row on the flange of the pterygoid. The palatine teeth rested on elevated platforms of bone, whose width, sharpness, and orientation varied between species. The orientation of the teeth in the jaws changed along their length, with the back teeth pointing backward. These palatal teeth, likely working in concert with a muscular tongue, would have helped Champsosaurus grip and swallow prey efficiently, ensuring that its fishy meals did not slip away. Fossilized skin impressions provide a glimpse of its external appearance. The scales were small, ranging from 0.6 to 1/10 of a millimeter, pustulate or slightly raised and rhomboid in shape. The larger scales were located along the sides of the body, becoming smaller as they moved toward the back. Interestingly, Champsosaurus did not have any osteoderms, the bony armor plates found in some related reptiles, suggesting a smooth and flexible body well suited for swimming. Champsosaurus belonged to a group called Neocoristodera, within the larger Coristodere lineage. Members of this group are known for their elongated snouts and expanded temporal arches. Neocoristoderas first appeared in Asia during the early Cretaceous, a time long before the end of the Mesozoic era, and are believed to have evolved in regions where aquatic crocodilians were absent. While the grouping itself is well supported, the exact relationships between its members remain somewhat uncertain, with recent studies showing a polytomy, meaning a branching of several species whose precise evolutionary order is not yet resolved. Champsosaurus was highly specialized for an aquatic life. Early research, particularly by Erichsen in 1985, suggested that the expanded temporal arches, which likely anchored powerful jaw muscles, combined with the elongated snout, allowed Champsosaurus to feed on fish in a manner similar to modern gharials. These adaptations enabled rapid and precise movements of the head and jaws, ideal for snapping up fish in fast-flowing water. A study in 2021 examined the neck vertebrae and found that the middle and rear sections of the neck were built to allow lateral, or side-to-side, movements. This adaptation indicates that Champsosaurus may have fed by sweeping its slender jaws sideways through schools of fish, a hunting style somewhat different from modern gharials, where lateral movement occurs primarily at the head-neck joint. Rather than relying on inertial feeding, where prey is temporarily released and then forced deeper into the throat by a rapid head motion, Champsosaurus likely used its tongue along with its palatal teeth to push prey down its throat. The position of the nostrils at the tip of the snout is particularly fascinating. Erichsen suggested that this placement allowed Champsosaurus to spend extended periods at the bottom of lakes or rivers, keeping its head angled upward so that the snout acted like a snorkel, enabling it to breathe while mostly submerged. However, later studies pointed out that the neck vertebrae likely had limited upward flexibility, which may have restricted this behavior. Champsosaurus shared its habitat with similarly sized aquatic crocodilians and in some locations during the Paleocene coexisted with another Neocoristodera, Simoedosaurus. Interestingly, in areas where Champsosaurus thrived, long-snouted, gharial-like crocodilians were absent. This suggests that these species occupied different ecological niches, reducing direct competition for food. Previous research identified 2 species of Champsosaurus from the Tulloch Formation in Montana. However, further analysis has indicated that these differences may actually reflect sexual dimorphism, meaning physical differences between males and females. Presumed female Champsosaurus individuals had more robust limb bones. In addition, these specimens often displayed fusion of the sacral vertebrae that was not caused by deformation, which may have played a role in reproduction. The combination of stronger limbs and fused sacral bones could have helped females move onto land to lay eggs, a vital adaptation for their survival. Allodaposuchus is a genus of ancient crocodiliform reptiles that lived in what we now know as southern Europe during the late part of the Cretaceous period, specifically during the Campanian and Maastrichtian stages, and possibly even as early as the Santonian stage. This places Allodaposuchus in a time frame stretching from approximately 83 million to 66 million years ago, a period when Europe was largely a collection of islands, surrounded by warm, shallow seas. During this era, the continent hosted a rich mosaic of ecosystems that range from floodplains and rivers to coastal swamps, and it is within these landscapes that Allodaposuchus thrived. These creatures are usually classified as non-crocodilian eusuchians, meaning that they are closely related to modern crocodiles, but are not considered part of the true crocodilian lineage. However, there is ongoing debate among paleontologists, with some experts suggesting that Allodaposuchus could represent one of the earliest forms of true crocodilians, placing it at a critical point in the evolutionary story of these formidable reptiles. Allodaposuchus is among the most commonly found crocodilomorphs from the late Cretaceous of Europe. Its fossils have been uncovered in multiple regions, including Romania, Spain, and France, providing a fascinating window into its distribution and ecology. These fossils include a range of material, from fragmentary bones to remarkably preserved skulls, each contributing pieces to the puzzle of this genus's anatomy, behaviour, and lifestyle. Unlike many modern crocodiles and alligators, Allodaposuchus was relatively small in size. Most species did not exceed lengths that would make them dominant predators in their habitats, and they were significantly smaller than the giant crocodilians that have become familiar in both the fossil record and in modern rivers and swamps. The largest specimen known from Allodaposuchus, however, belonged to an individual that likely measured around 3 meters in length, or roughly 9 feet and 10 inches, which is still large enough to command respect in its environment, but comparatively modest by modern standards. The skull of Allodaposuchus is one of its most distinctive features. In general, the skull is short, flattened and rounded, a shape that sets it apart from many other crocodilomorphs of the time, which often had long, narrow snouts adapted for specific prey. Among the various species of Allodaposuchus, there are notable differences in the shape and proportions of the skull. For instance, Allodaposuchus praestens, the type species, possesses a short-snouted or brevirostrine skull. In this species, the snout is approximately the same length as the skull table, which is the region of the skull behind the eye sockets, creating a compact and robust appearance. On the other hand, Allodaposuchus subjuniperus exhibits a more intermediate snout length, known as mesorostrine, where the snout extends beyond the skull table, giving it a slightly more elongated profile. These differences in skull shape likely reflect variations in feeding strategies, prey choice, or ecological niche among the species. One of the most defining characteristics of Allodaposuchus, which helps paleontologists distinguish it from related crocodilomorphs, is the unique orientation of a groove at the back of the skull called the cranio-quadrate passage. In most other crocodilomorphs, this groove is visible only when the skull is viewed from directly behind, but in Allodaposuchus, it is clearly observable even when looking at the skull from the side. This unusual feature has been a key anatomical marker in identifying fossils and understanding the relationships of Allodaposuchus within the broader group of crocodiliforms. It provides valuable insight into the internal anatomy of the skull, particularly the arrangement of bones and airways that may have influenced hearing, jaw mechanics, and even the way these reptiles held and used their heads in life. Among the known species, Allodaposuchus hulki stands out for its remarkable adaptations that suggest it may have been capable of spending significant amounts of time on land. This species is named after the Marvel Comics character, the Hulk, in reference to the robust and muscular nature of its skeletal remains, which indicates strong physical capabilities. The skull of A. hulki contains unusually large sinuses, structures not observed in any other living or extinct crocodilian. These sinuses may have served multiple purposes. One possibility is that they enhance the animal's ability to hear while out of water, allowing it to detect prey or threats across the floodplain environments in which it lived. Another likely function of these air-filled spaces was to reduce the weight of the skull, making it easier for the animal to support and move its head while walking on land. This would have been especially important for a species that may have spent long periods away from water, navigating the uneven terrain of temporary ponds and floodplain landscapes. The postcranial skeleton of A. hulki, particularly the bones of the forelimbs, also reveals adaptations for a semi-erect stance, a posture that is well suited for terrestrial locomotion. The scapula, humerus and ulna all exhibit strong muscle attachments, indicating that the forelimbs were capable of supporting the animal's weight efficiently and allowing it to walk or even trot across land. This terrestrial capability is further supported by the geological context of the fossils. Remains of A. hulki have been found in interbedded sandstones and marls, sediments that suggest the presence of ephemeral ponds in a large floodplain environment. The presence of charophyte algae in these sediments indicates that these ponds were temporary and far from permanent bodies of water, like lakes or rivers. It is plausible that A. hulki moved between these scattered ponds in search of food, relying on its ability to traverse land more extensively than other crocodilomorphs of its time. The history of the genus Allodaposuchus is closely tied to the work of Hungarian paleontologist Franz Nopcsa, who first named the type species Allodaposuchus precedens in 1928. Nopcsa discovered fragments of bones in the Veluara locality of the Haseg Basin in Romania, a region that dates back to the very end of the Maastrichtian stage, approximately 66 million years ago. His initial finds were fragmentary, yet they laid the foundation for subsequent research into this genus. Over the decades, additional fossils from Spain and France have been attributed to A. precedens, including several partial skulls discovered in deposits that are slightly older than those in Romania, dating to the Campanian stage. These discoveries suggest that the species persisted for several million years, surviving through significant environmental changes during the late Cretaceous. Research into Allodaposuchus has not been without debate and revision. A study conducted in 2013 suggested that the French and Spanish fossils originally assigned to A. precedens might actually belong to a new, unnamed species of Allodaposuchus, currently referred to as Allodaposuchus S. Earlier, in 2005, a separate study had proposed that these fossils were not part of Allodaposuchus at all, but instead represented several different genera of crocodilomorphs, and that the original Romanian material was too fragmentary to justify naming a distinct genus. This led to the suggestion that Allodaposuchus could be considered a nomen dubium, a term used by paleontologists for names that are dubious or insufficiently supported by diagnostic material. However, the 2013 study reaffirmed the distinctiveness of the Romanian fossils from other European crocodilomorphs, providing renewed support for the validity of Allodaposuchus as a genus. To address the issue of fragmentary material, a petition was submitted to the International Commission on Zoological Nomenclature in 2017 to designate the specimen Smubva 438 as the neotype, effectively replacing the original type specimen, which was considered non-diagnostic. This petition was approved in 2020, providing a more complete reference specimen for Allodaposuchus precedens and helping to stabilize the taxonomy of the genus. These efforts have allowed paleontologists to more confidently identify and compare Allodaposuchus fossils across Europe, even as new discoveries continue to complicate the picture. The diversity of Allodaposuchus expanded further with the discovery of a second species in 2013. Allodaposuchus subjuniperus was named based on a skull found in the late Maastrichtian Conque Formation, part of the Tremp group in the province of Huesca, Spain. Interestingly, the skull was discovered beneath a juniper tree, with the roots having grown among the bones, which inspired the species name subjuniperus, meaning under juniper in Latin. Initially, this species, along with the type species of a new genus called Aegisuchus A. fontesensis, was placed into a separate genus in 2016, based on differences that appeared sufficient to distinguish them from A. precedens. However, a phylogenetic analysis published in 2021 challenged this separation, suggesting that both A. fontesensis and A. subjuniperus may actually belong within the genus Allodaposuchus itself, alongside other species previously assigned to the genus Lohuecosuchus, namely L. megadontos and L. mechinorum. This example highlights the fluid nature of paleontological taxonomy, where new methods of analysis and new fossil discoveries continually reshape our understanding of evolutionary relationships. Further species were named as research progressed. In 2014, Allodaposuchus palustris was described based on a partial skull and other skeletal fragments from Maastrichtian age sediments of the Tremp Formation at a locality known as Fumania Sud in the southern Pyrenees. These remains provided an unprecedented opportunity to study not just the skull, but also the postcranial anatomy of Allodaposuchus, shedding light on its overall body structure and potential locomotor abilities. The following year, in 2015, Allodaposuchus hulki was formally named, based on fossils from the Casafabar locality of the same formation. The name, evocative of the strong and muscular comic book character, reflects the robust nature of the bones, suggesting a creature built for physical exertion, possibly capable of more terrestrial activity than most of its relatives. In 2021, Allodaposuchus palustris was further described by Blanco, based on fossils discovered in late Campanian age fluvial deposits at Velo-la-Bastide-Neuve in southern France, with the species name referencing the Ibero-Armorican island of the Cretaceous European archipelago, connecting the species to its paleogeographical context. The genus Aegisuchus, first described in 2016 with the type species Aegisuchus fontesensis, was named from fossils discovered at the Lo Hueco fossil site in Fuentes, Cuenca, Spain, with the Latin term fontis referring to the locality. Initially, Allodaposuchus subjuniperus was also assigned to this genus. However, the work of Blanco in 2021 proposed that these species should remain within Allodaposuchus, treating Aegisuchus as a junior synonym. Similarly, the genus Lohuecosuchus, established in 2015 with two species, L. megadontos and L. mecanorum from Spain and southern France, was also proposed by Blanco to be folded into Allodaposuchus, again as junior synonyms, reflecting the evolving understanding of the relationships among these European crocodilomorphs. Allodaposuchus is part of the clade Allodaposuchidae, a group whose precise placement in the crocodiliform evolutionary tree remains a topic of research and discussion. Some studies, such as those by Narvaez and colleagues, have considered Allodaposuchidae as the sister group to Hylaeocampsidae, with both together forming a clade that is itself the sister group to Crocodilia. Other analyses have suggested that Allodaposuchidae might represent an evolutionary grade leading towards true crocodilians, with Hylaeocampsidae occupying a more basal position. Yet other studies, including a comprehensive analysis in 2021 that incorporated postcranial anatomy, have placed Allodaposuchidae firmly within Crocodilia, demonstrating just how much debate and reinterpretation continues to surround this group. The ecology of Allodaposuchus, as inferred from fossil sites and anatomical features, paints a picture of a diverse and adaptable genus. While many species appear to have been semi-aquatic, relying on floodplains, rivers and ponds, some species like A. hulki may have been more capable of terrestrial life. The skeletal structure of these animals, with strong limb muscles and adaptations for both swimming and walking, indicates that they could have exploited a range of habitats, from temporary ponds in floodplains to more permanent water bodies. Their skull shapes, from short and robust to moderately elongated, suggest variations in diet and feeding strategy, potentially allowing multiple species to coexist without directly competing for the same prey. The presence of Allodaposuchus across multiple European regions and across several million years hints at its success and resilience in a world of shifting seas, islands, and climate changes. The discovery and ongoing study of Allodaposuchus species provide valuable insight into the evolutionary history of crocodiliforms in Europe. By examining both cranial and postcranial anatomy, paleontologists can reconstruct not just the physical appearance of these animals, but also their behavior, ecology, and interactions with their environment. Fossils from different regions, from the Haseg Basin of Romania to the Tremp Formation of Spain and southern France, allow researchers to trace the geographic spread and diversity of the genus, showing how these reptiles adapted to various local conditions and possibly dispersed across the island landscapes of Cretaceous Europe. Each new discovery, whether a skull fragment, limb bone, or partial skeleton, contributes to a growing picture of how Allodaposuchus lived, moved, and survived in a dynamic and often challenging environment. The study of Allodaposuchus also illuminates broader questions about the evolution of crocodilians and their relatives. By comparing cranial features such as the unique cranioquadrate passage and postcranial adaptations, scientists can explore how different lineages diverged and evolved specialized forms. Some species appear to have been more aquatic, while others show evidence of significant terrestrial capability, highlighting the ecological flexibility that may have contributed to their success. Debates over taxonomy, such as the distinction between Allodaposuchus, Aegisuchus, and Lohuecosuchus, reveal the complexity of interpreting fragmentary fossil records and the importance of careful anatomical and phylogenetic analysis. These discussions also emphasize how new discoveries and modern analytical techniques continue to refine our understanding of these ancient reptiles. Fossil evidence indicates that Allodaposuchus lived in a variety of environments that were shaped by the unique paleogeography of late Cretaceous Europe. The continent was largely a series of islands separated by shallow seas, creating a landscape of isolated habitats that fostered both endemism and diversity. Floodplains, ephemeral ponds, and river systems provided niches for semi-aquatic species, while more terrestrial adaptations, as seen in A. hulki, allowed some species to exploit land-based resources. The geological context of these fossils, including sediment types and associated flora and fauna, offers clues about the ecosystems in which Allodaposuchus lived, from the composition of the floodplain vegetation to the seasonal dynamics of temporary water bodies. These environments would have influenced not only the behavior and mobility of Allodaposuchus, but also its interactions with other contemporary reptiles, dinosaurs, and smaller vertebrates. The body size of Allodaposuchus species, while modest compared to some modern crocodiles, still allowed them to be effective predators and scavengers. A 3-meter-long individual, for instance, would have been capable of preying on fish, amphibians, small dinosaurs, and various invertebrates, while also avoiding larger predators. The structure of their limbs, tail, and body suggests a combination of swimming and walking abilities, enabling them to navigate diverse terrain and access different food sources. The variation in snout length among species likely reflects dietary specialization, with shorter snouts perhaps suited for crushing or seizing particular prey, and longer snouts allowing for more precise or rapid capture. The combination of these features illustrates a genus that was both adaptable and varied, capable of occupying multiple ecological roles in late Cretaceous Europe. The discovery of Allodaposuchus fossils has also contributed to understanding the faunal composition of the Cretaceous European archipelago. Sites such as Velo-la-Bastide-Neuve in southern France, Fumania Sud in the southern Pyrenees, and various localities in Romania provide snapshots of ecosystems rich in both vertebrates and invertebrates. The presence of Allodaposuchus alongside other reptiles, fish, amphibians, and dinosaurs highlights its role within these communities, suggesting interactions ranging from predation to competition. Fossil assemblages often include multiple species of Allodaposuchus, as well as other crocodiliforms, indicating that niche partitioning and ecological diversity were important factors in the survival and proliferation of these animals. Seasonal and environmental fluctuations, including temporary ponds and floodplain dynamics, would have further shaped their behavior, feeding strategies and dispersal patterns across the fragmented European landscape. The anatomical features of Allodaposuchus, particularly the unique cranial grooves and postcranial adaptations, allow paleontologists to reconstruct aspects of their sensory and locomotive capabilities. The cranioquadrate passage visible from the side of the skull may have implications for auditory function, feeding mechanics, or muscle attachment, although the exact significance remains a topic of investigation. Limb morphology, especially in species such as Aegisuchus, suggests a capacity for semi-erect terrestrial movement, while the overall body plan supports a combination of swimming and walking. These features demonstrate the versatility of Allodaposuchus in exploiting its environment, whether moving between isolated ponds, hunting along floodplains, or avoiding larger predators. Each anatomical trait provides a piece of the puzzle in understanding how these reptiles lived and adapted to the changing landscapes of late Cretaceous Europe. Anatosuchus was an amazing and unusual little crocodiliform, now completely extinct. The name itself hints at its most striking feature, a broad flattened snout that looks surprisingly like a duck's bill, a feature that sets it apart from most of its crocodiliform relatives. This remarkable genus was first discovered in the desert region of Gadufawa, in what is today Niger, a country in West Africa. The discovery was made known to the scientific world in the year 2003 through the work of a team of paleontologists led by the American scientist Paul Sereno, who published the initial description in the Journal of Vertebrate Paleontology. The primary species of this genus, known as Anatosuchus minor, carries the species name minor to highlight its relatively small body size compared to other crocodiliforms. The holotype, or the specimen used to formally describe the species, it is an exceptionally well-preserved juvenile skull with the lower jaws still connected, offering scientists an unusually clear glimpse into the anatomy of a young animal. This skull was unearthed from rock layers that sit at the upper part of the Elras Formation and the lower portion of the Echka Formation, formations which are known to date back to the early Cretaceous period, specifically around the late Aptian to early Albian stages, roughly 115 to 110 million years ago. Later, another specimen was discovered belonging to an adult Anatosuchus. This specimen included both the skull and much of the body skeleton, allowing researchers to see how this animal changed as it grew. Notably, the broad, flattened shape of the snout became even more pronounced in adults, showing that this duck-like feature developed with age. The frontmost bones of the snout, called the premaxillae, were wide and flat, forming a straight line across the tip of the snout. Each premaxilla held 6 small teeth that curved backward into the mouth, perfect for gripping prey. The structures where the premaxillae meet the nose, called the internarial processes, rose steeply towards the projecting nasal bones. These processes started wide, giving the external nostrils a flattened, compressed appearance from top to bottom. The premaxillae also helped form the floor of the nasal passages and had a small upward flange, which made the nostrils point slightly upwards and outwards, giving the animal a little protruding nose at the tip of its broad snout. Just behind the nostrils were smooth depressions, known as narial fossae, which further contributed to the characteristic flattened, wide look of the snout. Behind the premaxillae were the maxillae, which were by far the largest and most dominant bones in the skull. Each maxilla contained 19 small, backward-curving teeth. These bones had narrow edges along the teeth, called alveolar margins, which contrasted with their broad expanse and gave the head a rather rectangular shape. The maxillae extended above and below the openings in the skull called antorbital fenestrae, with the upper parts connecting to the nasal bones and the bones around the eye, including the prefrontal and lacrimal bones. The surfaces of the maxillae were textured with small pits and channels for nerves and blood vessels, although these textures were far less pronounced than on the nasal, frontal and parietal bones. Together, the maxillae and the palatine bones formed the roof of the mouth. The middle third of this palate curved upward, creating more space in the mouth cavity, while the outer thirds remained flat. Each maxilla had a narrow slit-like opening on the palate, and at the very back, the pterygoid and ectopterygoid bones contributed to the structure of the posterior palate and the lower jaw joints. The choanae, the internal openings of the nasal passages, were located as far back as possible without touching the suborbital fenestrae, and a thin wall of bone separated them. The nasal bones were long and fused along their entire length, running from just behind the internarial bar formed by the premaxillae to beneath the frontal bones. The lacrimal bones were L-shaped, reaching forward to meet the maxilla and downward to help form the eye socket. Small processes on the lacrimals allowed the attachment of palpebral bones, which acted like bony eyelids. Both front and back palpebrals were present above each eye. The prefrontal bones, shaped somewhat like a capital 1, sat between the nasals and lacrimals, effectively separating these bones while forming part of the skull roof. The frontal bones of the skull were fused into a single solid piece, as were the parietals, which formed the rear part of the skull roof. The suture between the frontal and parietal bones was intricate and interlocked tightly. In juvenile Anatosuchus, the width between the eyes was smaller than the width across the top of the skull, but in adults, this interorbital width expanded to nearly twice the width of the skull table. Above the brain case, the supratemporal fenestrae had distinctive corners, formed by projections of the frontal bone, a feature that became more pronounced with age. The small postorbital bones, slightly curved, helped anchor the posterior palpebrals. At the very back of the skull, the squamosal bones were triradiate, with thin forward processes meeting the postorbitals and backward processes extending down toward the brain case. The jugals, or cheekbones, had long forward arms but did not reach the antorbital openings. Small oval depressions sat below each eye. The quadratojugals fused partially with the quadrates near the jaw joints, but did not directly participate in the jaw articulation. The quadrates slanted backward and downward from the ear region to their lower ends. The brain case itself was well preserved in these specimens. Small triangular supraoccipital bones bore short vertical ridges and large lateral flanges. The paroccipital processes, connecting the squamosals and quadrates, showed a series of fine striations. The occipital condyles, which articulated with the vertebral column, tilted downward and were largely formed by the bassioccipitals. 3 eustachian openings were present on each side of the skull, including 2 on the basioccipitals and 1 between the basisphenoid and occipitalis. Running between the quadrate and pterygoid on each side were pairs of crests, adding strength to the brain case structure. The lower jaw was U-shaped to perfectly match the upper jaw. The dentary, or main lower jaw bone, carried 21 teeth on each side. As the jaw curved around the U-shape, the dentary became broader from side to side rather than top to bottom, thanks to wide, blood-rich shelves along the tooth row. The 2 dentary bones were interlocked at the front, making the jaw completely rigid. At the back, the dentary formed part of the external mandibular opening, while the angular and surangular bones extended up to form the coronoid process. The surangular dominated the jaw joint, which was saddle-shaped with no forward or backward lips, though a prominent attachment crest extended behind and below the joint. Anatosuchus's teeth were small, conical and curved inward, and they were relatively unworn, suggesting that the animal did not chew extensively, but likely used them to grasp or cut prey. Most teeth had tiny ridges, called carinae, on their surfaces. The very front of the lower jaw, near the dentary symphysis, was toothless for a short distance of roughly 11 millimeters, creating a sharp edge that may have worked in tandem with the front premaxillary teeth to slice into food. The largest teeth were found at the corners of the jaws, likely used for puncturing and holding struggling prey. Anatosuchus exhibits a skeletal structure that is both intricate and unusual, revealing much about its anatomy, movement, and possible lifestyle. Its vertebral column is particularly informative, giving insights into how this tiny crocodile-like creature held itself and moved through its environment. At the front of its spine, it possessed a parotless vertebra, a specialized bone that precedes the first true neck vertebra. Following this, there were 8 cervical vertebrae, forming the flexible neck region, and probably 16 dorsal vertebrae in the back, although only 15 of these have been preserved in the fossil record. Toward the rear of the trunk, 2 sacral vertebrae connected the spine to the hip region, completing a skeleton well suited for a small, agile predator. The shapes of these vertebrae provide fascinating details. The dorsal vertebrae, those forming the back, are amphicolous, meaning they are concave at both ends, a feature that likely contributed to a flexible yet sturdy backbone. Interestingly, the cervical vertebrae, the neck bones, do not have hypopophyses, the downward projecting processes that are common in some other reptiles. This absence hints at a unique neck structure and range of motion for Anatosuchus. The proatlas itself is an intriguing structure, shaped like an upside-down letter V, complete with a dorsal keel running along the midline. Despite being a small bone in the grand scheme of the skeleton, it is surprisingly large when compared to the atlas vertebra it precedes, which is itself composed of 2 separate neural arches that help form the first movable joint of the neck. Following the atlas, the axis vertebra, which serves as the pivot for head rotation, has a low neural spine that is almost rectangular in shape. Moving down the neck, the neural spines on the cervical vertebrae increase in height. The third cervical vertebra has a spine that is roughly twice as tall as it is long, while the 7th cervical spine is nearly 5 times taller than its length. This progressive increase in spine height along the neck may have supported strong neck muscles, allowing Anatosuchus to lift or twist its head with ease. The dorsal vertebrae of the back are comparatively long relative to their width, with each vertebra's length always more than half the distance across its lateral projections, known as transverse processes. This elongated shape may have provided both strength and flexibility to the back, aiding movement and stability. The ribs of Anatosuchus show a remarkable diversity in form. The ribs attached to the atlas and axis vertebrae are straight, simple structures, while the ribs of the remaining cervical vertebrae are shorter and have a triradiate or 3-pronged shape. The ribs of the back or dorsal ribs curve downward after they extend past the protective bony armour, forming a slight flange along the front edge. Ribs located closer to the rear of the animal have only a single head connecting them to the vertebrae. The gastralia, or belly ribs, are poorly preserved in the fossil record, especially in the region between the shoulder and pelvic girdles, leaving some questions about the exact structure of the underbelly. The body armour of Anatosuchus, its osteoderms, appears to have been limited to the dorsal surface of the body. These bony plates were arranged in pairs, with each pair corresponding to 1 vertebra in the back, and in some cases extending over up to 3 neck vertebrae. The articulation between rows of osteoderms was minimal, involving only a slight overlap at the edges of adjacent rows. Each osteoderm was trapezoidal in shape and pitted with small depressions, likely providing both protection and a lightweight structure. The plates attached to the vertebrae through a central facet that accommodated the top of the neural spine, creating a firm but flexible armour along the back. This careful arrangement suggests a balance between defence and mobility, allowing Anatosuchus to remain nimble despite its protective covering. Moving to the shoulder and forelimb region, the scapulae, or shoulder blades, are broad but do not flare widely at their outer edges. The distal ends of the blades are tucked beneath the osteoderms, implying that the shoulders were well integrated with the protective armour. The coracoids, another part of the shoulder girdle, are elongated, providing strong attachment points for muscles controlling the forelimbs. The humeri, or upper arm bones, are long and straight, yet slender, with their width measuring less than 10% of their total length. Fossae, or depressions, on the humeri indicate where the olecranon processes of the elbows would fit, suggesting that the forelimbs could be held in a relatively straight supportive posture. The radius and ulna, the bones of the forearm, show interesting adaptations. The radii have pronounced flaring at their proximal ends but are noticeably shorter than the ulnae, which extend along the edges of the radiales, the wrist bones. The ulnae themselves are curved and relatively robust. The radiales are strong, heavy bones, almost as wide as the radii, while the ulnares, counterparts in the wrist, are poorly preserved. The manus, or hand, of Anatosuchus is large and unusual. Particularly notable is the fourth digit of the hand, which has 6 phalanges instead of the usual 4 found in most crocodilomorphs. Despite the increased number of phalanges, the overall length of this digit is only about 80% of the other fingers. This is due mainly to the elongated unguals, or claw bones, which are arched strongly and have narrow grooves along their length for attachment of tendons or other soft tissues. The purpose of these unusual features remains unclear, but they may have provided specialized functions, such as gripping or manipulating prey. From a classification standpoint, Anatosuchus has undergone some taxonomic re-evaluation. Initially, it was considered closely related to Carnufex, forming a subgroup within a smaller, well-defined portion of Notosuchia, itself thought to be monophyletic, meaning it descended from a common ancestor without including unrelated lineages. Later research, however, challenged this view, suggesting that Anatosuchus is not closely tied to Carnufex, but instead belongs to the family Uruguaysuchidae, a distinct lineage of small crocodiliforms with their own unique traits and evolutionary history. As its species name, minor, implies, Anatosuchus was a very small crocodilomorph. Adult individuals are estimated to have reached a body length of only around 70 centimeters, which is approximately 28 inches. One of its most distinctive features is its wide, flat snout, reminiscent of a duck's bill, giving it a peculiar and memorable appearance. Despite this unusual shape, its jaw and teeth suggest that Anatosuchus primarily fed on small aquatic animals, such as tiny fish, invertebrates, or amphibians, making it a nimble predator in its watery habitat rather than a creature designed for tackling large prey. The combination of its small size, broad snout, specialized teeth, and unique skeletal adaptations paints a picture of a highly specialized little crocodiliform, perfectly suited to a life in shallow waters and wetlands. Its elongated neck and strong cervical spines would have allowed it to reach and snatch prey with precision, while its flexible back and lightweight armor provided protection without sacrificing agility. The unusual structure of its forelimbs and hands, including the extended fourth digit, hints at behaviors or hunting strategies that remain mysterious, but undoubtedly contributed to its survival in a competitive ecosystem. In examining Anatosuchus, paleontologists are provided with a rich case study in the diversity of small crocodiliforms during the late Cretaceous. Its detailed vertebral structure, specialized limbs, and armored back demonstrate the remarkable variety of adaptations that evolved in these miniature crocodile relatives. Every vertebra, rib, and osteoderm tells a story of how this creature moved, hunted, and defended itself, offering glimpses into an ancient world where even the tiniest predators had their own unique ways of thriving. The intricacies of its skeletal system, from the inverted V-shaped proatlas to the elongated unguals of the fingers, underscore the sophistication of evolutionary design, even in creatures no larger than a modern-day dog. Through the study of Anatosuchus, researchers can appreciate the delicate balance between protection, flexibility, and functionality that shaped its body. Its dorsal armor provided a shield against predators, yet left enough mobility for swimming and hunting. Its slender, elongated forelimbs and strong hands suggest nimbleness and dexterity, while the growth pattern of its cervical spines indicates powerful neck muscles capable of precise and rapid movements. This combination of features highlights a small but formidable predator of freshwater environments, whose tiny frame belied a complex and capable anatomy. Carnufex is an extinct type of crocodilomorph, a distant relative of modern crocodiles, that lived in what is now North America during the late Triassic period. This fascinating genus was first officially described in the year 2015 by a team of paleontologists led by Lindsay Zano, who, together with her colleagues, gave it the scientific name Carnufex carolinensis, which translates to Carolina butcher. The name reflects both its probable predatory lifestyle and the place where it was discovered, the state of North Carolina. Only 2 specimens of this remarkable creature have been found so far. The first is the holotype, labelled NCSM 21558, which includes a partial skull and portions of the skeleton. The second, referred to as NCSM 21623, consists of part of a humerus, or upper arm bone, smaller than that of the holotype. Both specimens come from the Pekin Formation, a sequence of rock layers formed during the Carnian stage of the late Triassic, roughly 231 million years ago. The holotype specimen, NCSM 21558, was discovered in a striking red river-deposited conglomerate rock found in the middle to upper levels of the Pekin Formation in North Carolina. In 2015, Zano, along with Susan Dreimeler, Sterling Nesbitt, and Vincent Schneider, described this fossil in a Scientific Reports article, officially introducing Carnufex carolinensis to the scientific community. This discovery revealed that the holotype preserves many parts of the animal's skeleton, including sections of the skull such as the premaxilla, maxilla, lacrimal, and jugal bones. Portions of the lower jaw, including the angular and articular bones, were also present, along with an atlantal intercentrum from the neck, several neural arches from the cervical and dorsal vertebrae, a collection of ribs, and an upper arm bone, the humerus. The referred specimen, NCSM 21623, consists only of a fragment of the humerus, which is noticeably smaller than that of the holotype. These fossils were later studied in more detail in a 2016 article in PLOS One by Dreimeler and Zano. Estimating the size of Carnufex is not straightforward. The skull and humerus of the holotype show unusual proportions. If one tries to predict body size based on the skull alone, it suggests a much larger humerus than what is preserved. Conversely, estimating size from the humerus would indicate a much smaller skull. This discrepancy suggests that the skull may have been unusually large, the forelimbs unusually small, or perhaps both traits were true. Using comparisons with other small crocodilomorphs from the same region, such as Deinosuchus and an undescribed species labelled NCSM 21722, Zano and colleagues estimated that the holotype was about 3 meters long, which is roughly 9 feet and 10 inches, and about 1.5 meters tall, or around 4 feet and 9 inches. However, the holotype was not fully grown, as indicated by the unfused sutures in its vertebrae, meaning it likely grew even larger. Alongside Redondavenator and another early crocodilomorph identified as CM 73372, Carnufex was among the largest crocodilomorphs of the Triassic, showing that some of the earliest members of this group were already evolving considerable size. This also challenges earlier ideas that features typical of crocodilomorphs only appeared after body size decreased, suggesting instead that these traits could have emerged even in large species. Carnufex displays a fascinating combination of traits. Some features are typical of crocodilomorphs, while others resemble more distant relatives such as Postosuchus. At the same time, it has numerous unique characteristics, known as autapomorphies, which set it apart from all its close relatives. The skull was large, elongated, and marked with heavy textures in certain regions, while the forelimbs were relatively small compared to the body. The premaxilla, forming the front of the upper jaw, was low and held at least 6 slender, serrated, and recurved teeth. At the back of this row, there was a distinctive notch, similar to what is seen in Dromaeosuchus. Like other archosaurs, the premaxilla also contained a palatal process, a projection that contributes to the roof of the mouth. In Carnufex, there is a noticeable gap in this process, which may have created a small hole in the palate, possibly to accommodate a large 4th tooth from the lower jaw. The maxilla, or main upper jaw bone, featured a long ascending process, a vertical branch that maintained a consistent height along its length. In contrast, other pseudosuchians either have a shorter ascending process or one that changes in height along the bone. The lower branch, called the posterior process, was even longer and contained at least 15 serrated knife-like teeth, which were convex in the front and slightly concave at the rear. This posterior process was narrow at the front, circular in cross-section, and became deeper and thinner toward the back, a trait unique to Carnufex among closely related loricatans. Along this process ran a sharp ridge that ended at the rear lower corner of the anteorbital fenestra, the large triangular opening in front of the eye socket. This anteorbital fenestra was unusually large and elongated in Carnufex. Its upper rear corner sat above the lower rear corner, giving the rear edge a vertical orientation rather than the forward-sloping shape seen in other early crocodilomorphs. The lacrimal bone, near the front of the eye socket, was deeply cut by the antebetal fossa, a shallow basin surrounding the fenestra. The edge of this fossa was marked by a rough ridge with a small forward-pointing prong, similar to structures seen in some theropod dinosaurs. The outer surface of the jugal bone, forming part of the cheek, was covered in pits and ridges. Its front portion was tall and unusually smooth and rounded, while the rear portion was bifurcated, splitting into a large tapering branch and a smaller triangular one. This bifurcated structure is seen in other early crocodilomorphs and some dinosaurs, but in Carnufex the two branches are unequal in size. The angular, forming part of the lower jaw, was thin and slender with subtle branching textures. A prominent ridge on its outer rear portion likely supported the pterygoideus ventralis muscle, a trait rarely seen in other crocodilomorphs except in Deinosuchus. The articular, which forms the joint at the back of the jaw, was similar to that of other crocodilomorphs, featuring a saddle-shaped jaw facet, a deep groove for the cauda tympani nerve, and a small upward projection at the rear. It also had a small inward-pointing process similar to more primitive pseudosuchians like Purussaurus, though in Carnufex this projection was a small conical peak rather than a large pronounced structure. The cervical or neck vertebra of Carnufex is an extraordinary and intricate structure, reflecting a level of complexity that immediately highlights its importance in the anatomy of this ancient crocodilomorph. The neural arch, which forms the upper portion of the vertebra and surrounds the spinal cord, is particularly elaborate. It is adorned with no fewer than 9 laminae, which are thin, plate-like ridges that extend across different parts of the bone, forming connections and providing structural reinforcement. Between these ridges lie 12 distinct fossae, which are deep depressions or pits that likely serve to reduce weight without compromising strength, as well as to accommodate soft tissue or facilitate articulation with adjacent bones. The neural spine rising from the top of the arch is exceptionally tall relative to the rest of the vertebra. After rising vertically for a short distance, it bends backward at an angle of approximately 30 degrees, giving the neck an appearance of both height and flexibility. Extending outward from the sides of the cervical vertebra are the diapophyses, the bony projections that served as attachment points for the ribs. These projections are elongated vertically and extend to the sides, though their lateral reach is relatively modest compared to some other archosaurs. At the rear of the vertebra, the postzygapophyses, small, articular processes that connect one vertebra to the next, project downward at their edges. Unlike some related species, these postzygapophyses do not meet or converge at their bases. Instead, their foundations are separated by a narrow U-shaped gap, a feature that sets Carnufex apart from several other early archosaurs. In many archosaur species, the rear projection of the postzygapophyses forms a structure called the hyposphene, which provides additional stability to the spine. In contrast, although Carnufex exhibits a similar feature, the lack of convergence at the base marks a subtle but important difference. Interestingly, very few early pseudosuchians have preserved enough of the atlas, the first cervical vertebra, to allow detailed comparison with the crescent-shaped atlantal intercentrum found in Carnufex, highlighting the rarity and scientific value of this fossil. Moving down the vertebral column to the dorsal, or back vertebrae, the neural arch retains some similarities to the cervical structure, but there are several notable differences. The diapophyses in the dorsal region are much shorter than those of the neck and do not project as far laterally. The zygapophyses, which are the paired articular surfaces connecting one vertebra to another, lie in a more level orientation, providing stability along the back while permitting controlled motion. Overall, the dorsal neural arch is less intricate than its cervical counterpart. It has fewer laminae and fossae, reflecting a simplification of the vertebrae further down the spine. Among these features, a subtle hyposphene can be observed, though it is less pronounced than in some other reptiles. This feature may represent an intermediate evolutionary stage, bridging the gap between earlier archosaurs like Purussaurus, which possess a strongly developed hyposphene in their dorsal vertebrae, and later crocodilomorphs, which entirely lack this structure. The neural spine of the dorsal vertebra is slightly expanded from front to back at its tip, a feature reminiscent of non-crocodilomorph archosaurs. Unlike some of its relatives, however, it does not form a lateral expansion known as a spine table. Beneath the neural arch, an asymmetrical projection can be seen, which might represent an unusual pathological condition rather than a normal anatomical feature. The ribs preserved alongside these dorsal vertebrae are comparable to those of other paracrocodilomorphs, suggesting a broadly similar body plan and rib articulation to its close relatives. The forelimb of Carnufex is particularly intriguing, with the humerus, or upper arm bone, revealing a combination of primitive and unique characteristics. The humerus is relatively short, featuring a constricted shaft that gives it a slender appearance in contrast to the broader ends. Its distal or far end is strikingly wide, about 3 times the width of the shaft, compared with other crocodilomorphs, which typically exhibit a distal end only twice as wide. Along this distal end, the humerus displays an ectopicondylar groove and a supinator process, features that are absent in most other members of its clade. Perhaps most distinctively, Carnufex exhibits a pronounced crest along the rear edge of the ectopicondylar groove, a feature not found in any of its known relatives. These anatomical details suggest a close resemblance to Purussaurus, a related genus of large predatory pseudosuchians, rather than to the more derived crocodilomorphs that evolved later. This combination of primitive and distinctive traits in the forelimb highlights Carnufex as a fascinating example of early crocodilomorph evolution, showing both retention of ancestral characteristics and unique adaptations. From a broader perspective, Carnufex occupies an important position in the evolutionary tree of crocodilomorphs, a group that encompasses all Suchians more advanced than the Rauisuchidae. Phylogenetic analysis conducted by Zano and colleagues indicates that Carnufex represents one of the most basal members of this lineage, meaning that it retains many features of the earliest crocodilomorphs, while providing a critical window into the early diversification of this successful group. Alongside an unnamed genus, Carnufex stands at the base of the crocodilomorph tree, bridging the gap between earlier, more primitive pseudosuchians and the later, highly specialized crocodilomorphs that would dominate Mesozoic and Cenozoic ecosystems. The fossil of Carnufex comes from the Pekin Formation, a late Triassic deposit situated in the Deep River Basin, spanning the modern-day states of North Carolina and South Carolina in the United States. This formation dates back to the Carnian stage of the late Triassic, approximately 231 million years ago. It is the oldest known member of the Chatham Group, a sequence of rock layers that preserves a unique snapshot of terrestrial life during this dynamic period of Earth's history. The specific locality where Carnufex was discovered is a boulder field, and the characteristics of the surrounding rock suggest that the region once consisted of a channel or alluvial deposit, where rivers and streams would have transported sediments and shaped the landscape. During the Carnian, this area would have lain near 2 degrees north of the equator, implying a warm, tropical environment that supported a diverse array of plants and animals. Although much of the fauna from the Pekin Formation has yet to be formally described, preliminary studies indicate a fascinating ecosystem. In addition to Carnufex, the formation preserves the remains of a newly identified Etosaur, another crocodilomorph whose genus has not yet been named, and a Traversodont previously assigned to Borogomphidon. There is also evidence of a new Dicynodont, adding to the diversity of herbivorous species present. Fossils indicate that Carnufex was likely the largest carnivorous species known from the formation, suggesting a role as a top predator. However, its perceived dominance may partly reflect a sampling bias. Larger predators, such as Rauisuchids, may have existed in the same ecosystem, but remain undiscovered due to the incompleteness of the fossil record. As a result, researchers have cautiously suggested that Carnufex was probably part of a broader predator guild, a group of coexisting carnivores that shared resources and occupied overlapping ecological niches, rather than being the sole apex predator. Terrestrisuchus was a tiny ancient relative of modern crocodiles, representing one of the earliest forms of crocodilomorphs, the group that would eventually give rise to today's crocodilians. This little creature measured roughly 76 centimeters in length, which is approximately 30 inches, though some estimates, based on younger individuals, suggest it might have grown to over 1 meter, or slightly more than 3 feet, in full adulthood. Despite its small size, Terrestrisuchus was a remarkable predator, living entirely on land, a trait that set it apart from the semi-aquatic habits of today's crocodiles and alligators. Fossils of this tiny reptile have been discovered in Wales and in the southern regions of England, dating back to the very end of the late Triassic period, during a time known as the Ratian, roughly around 211 to 200 million years ago. The genus is represented by a single species, known scientifically as Terrestrisuchus gracilis, with gracilis aptly meaning slender in Latin, reflecting its long, delicate limbs and sleek, agile body. Terrestrisuchus thrived on a string of low-lying tropical islands that made up what is now southern Britain. These islands were dotted with other small dinosaurs, reptiles and rhynchocephalians, a group of lizard-like creatures that were abundant at the time. The fossil record of Terrestrisuchus is particularly rich because it lived on limestone karst islands, which are landscapes full of natural caves, fissures, and sinkholes. These geological features acted like natural traps and protective vaults, preserving the remains of Terrestrisuchus and many other island-dwelling reptiles, often in remarkable detail. This crocodilomorph was small, slim, and lightweight, with exceptionally long legs that hinted at its speed and agility. Its skull was narrow and elongated, ending in a pointed triangular snout that bristled with sharp, curved teeth, ideal for grasping small prey. The upper jaw followed a straight line without a gap, or diastema, between the front and side teeth, while the lower jaw's long, slender bones curved gently upward toward the front, giving the mouth a graceful predatory profile. Unlike modern crocodiles, the eyes of Terrestrisuchus were supported by a sclerotic ring, a circle of small bones that help maintain the shape of the eye, similar to structures seen in birds and some dinosaurs. The body of Terrestrisuchus was relatively short and shallow, but it was reinforced with a series of paired bony plates called osteoderms running along its neck and back. These osteoderms were shaped like leaves, longer than they were wide, each with a prominent forward spur that interlocked with the plate in front, forming a rigid yet protective armour that supported its body on land and limited twisting of the spine. Its hips were distinct from those of modern crocodilians, featuring a long pubis bone, and the belly was protected by tightly packed gastralia, or belly ribs. One of its most striking features was its extraordinarily long tail, roughly twice the length of its head and body combined, containing about 70 vertebrae. This tail likely served as a dynamic counterbalance, allowing Terrestrisuchus to rear up and possibly sprint on its hind legs for short bursts, an adaptation seen in some fast-running reptiles. The limbs of Terrestrisuchus were unlike those of any modern crocodilian. They were very long relative to the body and positioned directly under the torso rather than sprawling to the sides. The structure of the ankles and the elongated bones of the hands and feet indicate that Terrestrisuchus walked and ran on its toes, a stance known as digitigrade. Its metacarpal and metatarsal bones were tightly pressed together, reminiscent of the limbs of swift dinosaurs, showing that Terrestrisuchus was built for speed and capable of highly cursorial or fast-running locomotion. The pisiform bone in the wrist, comparatively small, suggests limited flexibility, unlike both early relatives such as Protosuchus and modern crocodilians. Reconstructions of Terrestrisuchus have varied. Some researchers, like Crush, depicted it as a quadruped with hind limbs longer than its forelimbs, its hips held above the shoulders, giving it a slightly crouched posture. Others argue, based on limb proportions and the geometry of its femur, that it might have been able to run bipedally at times, though this has been debated extensively in the scientific literature. Quantitative studies examining limb robustness tend to support a primarily quadrupedal stance, while analyses of femoral cross-sections indicate that brief bipedal movement may have been possible. Among its most unique traits was the structure of its hips. The hip socket, or acetabulum, was perforated, forming a true opening between the bones, a feature otherwise seen only in dinosaurs and a few early crocodilomorphs. This allowed the femur or thigh bone to articulate in a buttress erect posture, facing inward toward the body at a right angle to the leg. This arrangement differs sharply from the pillar erect stance found in most other crocodile line archosaurs, where the leg bones point straight down. The buttress erect configuration, combined with a backward-pointing calcaneal tubercle on the heel, ensured that Terrestrisuchus maintained a permanently upright stance and limited its body to a forward-facing upright gait. The story of Terrestrisuchus, one of the tiniest and earliest relatives of modern crocodiles, begins in the spring of 1952, when Professor K. A. Kermack and Dr. Pamela Lampler Robinson made a remarkable discovery. In a small quarry called Pantyffynon, located near the town of Cowbridge in Glamorgan, South Wales, they uncovered a set of ancient fossils embedded in the rocky earth. These fossils, carefully excavated from layers of sediment that had long been hidden within the limestone, immediately caught the attention of the scientific community. The following year, on the 8th of October 1953, Kermack presented their finds to the Linnean Society of London. He proposed that the remains belonged to a primitive crocodile or crocodile ancestor, a remarkable creature that seemed to bridge the gap between the crocodiles we know today and the Triassic reptiles known as decodonts. At that time, no protective bony plates called osteoderms had been identified among the fossils. Kermack speculated that this absence might indicate a form of missing link, a transitional stage in crocodilian evolution. The fossils they discovered were exceptional in their preservation, including several articulated partial skeletons, which meant that many bones were still connected in their original positions, alongside numerous isolated bones scattered throughout the sediment. Despite the significance of the discovery, Kermack did not immediately give the animal a formal scientific name or designate a type specimen, as the careful preparation of the fossils was still underway. It was not until more than 3 decades later, in 1984, that the fossils received their official description by paleontologist P.J. Crush. The genus was named Terrestrisuchus, a title chosen to emphasize its likely terrestrial lifestyle, as opposed to the semi-aquatic habits of modern crocodiles. The species was given the name gracilis, taken from the Latin word meaning slender or graceful, a nod to the animal's light and elegant build. The Pantiphynon quarry itself is mostly made up of limestone dating to the Carboniferous period, an ancient layer of rock formed hundreds of millions of years ago. However, the fossils of Terrestrisuchus were found in much younger Triassic sediments that had filled cracks and fissures within this limestone, including sandstones and marls. For many years, scientists debated the exact age of these deposits. Older studies suggested that they might belong to the Carnian to Norian stages of the late Triassic. Later, more precise analyses using fossil pollen, known as palynology, indicated a younger Ratian age, placing the creature very close to the very end of the Triassic period. This estimate was further supported by the discovery of other Ratian index fossils, such as small crustaceans called conchostracans, and by studies of the surrounding rock formations. Terrestrisuchus fossils have also been found in several other late Triassic fissure deposits across South Wales and the Bristol area. In Wales, additional material was recovered from the Ruthin quarry, while in the Bristol region, fossils came from the Titherington and Cromwell quarries, with a possible specimen from Durdham Down. In England, these remains were preserved within a rock formation known as the Magnesian Conglomerate. Originally, all Terrestrisuchus specimens were stored at University College London, but they were later transferred to the Natural History Museum in London, where they remain carefully curated today. When it was first classified, Terrestrisuchus was placed in a suborder of early crocodilomorphs called Sphenosuchia. This group consisted of several long-legged, small-bodied early relatives of crocodiles, and was thought to represent a side branch of the crocodilomorph family tree, separate from the line that led to modern crocodilians. However, this classification was made before modern methods of evolutionary analysis, known as cladistics, were developed. Later studies revealed that Sphenosuchia was not a natural grouping. Instead, it was a paraphyletic grade, a series of basal crocodilomorphs that eventually gave rise to the more advanced crocodiliforms. Even so, Terrestrisuchus consistently appears within this basal grade in evolutionary analyses. When Crush described Terrestrisuchus in 1984, he noticed a close resemblance to a German Sphenosuchian called Allodaposuchus. He therefore created a new family, Allodaposuchidae, to include both genera under the umbrella of Sphenosuchia. However, after the rise of cladistics, few scientists continued to use the name Allodaposuchidae, in part because some suggested that Terrestrisuchus and Allodaposuchus might actually be the same animal. Early analyses, such as the work by Sereno and Wild in 1992, grouped the two together along with a South African form called Litagosuchus. More recently, in 2017, Liardi and colleagues also found a similar clade, supporting Crush's original idea of a closely related group. Finally, in 2023, Speakman formally defined this clade as Allodaposuchidae in a phylogenetic study. Just 4 years after Terrestrisuchus was named, in 1988, paleontologists Michael Benton and James Clark suggested that it might represent the juvenile form of Allodaposuchus, making Terrestrisuchus a junior synonym. They argued that the differences identified by Crush were not sufficient to separate the two genera. However, Sereno and Wild rejected this idea in 1992, claiming they had found additional distinctions. Later in 2003, David Allen examined the fossils and initially believed that the differences could be explained by juvenile growth patterns. Yet, by 2010, in his unpublished doctoral thesis, Allen had reversed this opinion, concluding that Terrestrisuchus and Saltoposuchus were indeed separate animals. A comprehensive re-evaluation in 2013 supported this conclusion. The evidence suggested that Terrestrisuchus was distinct, based on its unique geographic and stratigraphic range, as well as differences in vertebral fusion patterns and hind limb proportions during growth. Terrestrisuchus lived several million years after Saltoposuchus, and subsequent studies, including a detailed redescription of Saltoposuchus in 2023 by Stefan Speakman, confirmed numerous morphological differences that could not be explained by growth or individual variation. Despite their differences, the two genera remain close relatives, forming the Saltoposuchidae clade alongside Dakosaurus. Terrestrisuchus had thin, sharply serrated teeth, which strongly suggest that it was a meat-eater, a carnivore that hunted other animals. Like many of its early crocodilomorph relatives, it probably did not specialize in a single type of prey, but instead hunted a variety of small to medium-sized animals, chasing them down with agility and persistence. The very structure of its hip bones, especially the long pubis, reveals that these bones were tightly fused together, unlike in modern crocodiles where the pubis can move. This means that Terrestrisuchus could not breathe using the same hepatic piston system that modern crocodiles employ, where the liver helps pump air through the lungs during breathing. Furthermore, the size and shape of its eye socket and the ring of bones within its eyes, known as the sclerotic ring, indicate that Terrestrisuchus was active at intervals throughout the day and night, a lifestyle referred to as cathemeral, rather than being strictly diurnal or nocturnal. Looking closer at the tiny structure of its limb bones, scientists have discovered that they were rich in blood vessels and packed with a type of bone tissue called fibrolamellar bone, which consumes a lot of energy to form. This combination suggests that Terrestrisuchus grew relatively quickly compared to other archosauriforms, and even to some of its pseudosuchian relatives, pointing to a metabolism that was more elevated, perhaps closer to warm-blooded, than the slower metabolism of modern crocodiles. However, another related sphenosuchian called Hesperosuchus shows a slower growth rate more similar to that of living crocodiles. This contrast raises the possibility that the rapid growth seen in Terrestrisuchus might have been due to the fossils studied being young, fast-growing individuals, while fully grown adults may have grown more slowly and had a more moderate metabolism. Unlike most basal crocodilomorphs, which are usually found in inland floodplains, Terrestrisuchus appears to have lived near the coast. During the late Triassic period, the area that is now the Pantyfinnon Quarry and surrounding quarries formed part of a chain of islands stretching across southern Wales and into the region that is now Bristol. These islands were covered in forests and featured rugged limestone landscapes with fissures, sinkholes, and deep caverns carved out by erosion. The long limbs and nimble build of Terrestrisuchus would have made it especially well suited to navigating this complex rocky terrain. On this ancient island, Terrestrisuchus shared its home with a fascinating cast of other prehistoric creatures. Among them was the equally long-legged and mysterious pseudosuchian Enigma spina, the plant-eating sauropodomorph dinosaur Pantydraco, and the predatory cheilophysoid theropod Pendrig. Small relatives of modern tuataras, known as rhynchocephalians, were extremely abundant and included at least 3 known species: Clevosaurus cambrica, Diffidontosaurus, and 1 or 2 others that have yet to be formally named. These small reptiles likely made up a significant part of Terrestrisuchus's diet, a fact supported by bite marks on some Clevosaurus bones that may have been left by this predator. Despite its predatory nature, Terrestrisuchus was not very common on the island, which fits the typical pattern of predators being relatively rare compared to their prey in an ecosystem. Apatosuchus is a genus of extinct reptiles that lived during the late Triassic period, a time over 230 million years ago when the Earth was a very different place. These creatures belong to a larger group of reptiles known as pseudosuchians, which are relatives of modern-day crocodiles and their extinct kin. The late Triassic was a world in flux, full of new types of reptiles and early dinosaurs, and Apatosuchus represents one of those small, specialized creatures that roamed the land during this tumultuous period in Earth's history. Its discovery and subsequent studies have provided important, if puzzling, glimpses into the early diversification of archosaurs, the great group that would later give rise to crocodiles, pterosaurs, and dinosaurs. The type species of this genus is known as Armadillosuchus grantii. The first scientific description of this species was made in the year 1894 by the British paleontologist E.T. Newton, a time when paleontology was still developing as a formal science, and the study of ancient reptiles was rapidly gaining attention. Newton's work was based on fossils unearthed in the northeastern region of Scotland, particularly from a geological unit known as the Lossiemouth Sandstone Formation. This formation, composed of sandstones, siltstones, and other sedimentary rocks, preserves a window into the environment of the latest Carnian stage of the late Triassic, roughly around 231 million years ago. Newton's description included 4 individual specimens, which collectively allowed him to reconstruct a portion of the anatomy of Armadillosuchus and recognize it as a distinct genus. The most significant of these fossils was the holotype specimen, catalogued as BMNHR 3139, which included a skull and parts of the postcranial skeleton, the bones behind the skull that make up the body, including the vertebrae and limb elements. The initial discoveries in Scotland provided the first tangible evidence of Armadillosuchus, but paleontologists soon wondered whether these creatures were limited to that part of the world, or if they had a broader geographic distribution. A major breakthrough came a century later during the spring of 1995, when the American paleontologist Paul E. Olson conducted a field expedition to the lower layers of the New Haven Formation in Connecticut, in the eastern United States. The New Haven Formation is a sedimentary rock unit that records a slightly younger portion of the late Triassic than the Lossiemouth sandstone, corresponding to the Nourian stage, which occurred roughly between 223 million and 215 million years ago. During this expedition, Olson discovered a partial skull among other scattered bones, and after careful preparation and analysis, the fossils were formally described in the year 2000. This discovery was remarkable because it represented the first record of Armadillosuchus outside of Scotland, demonstrating that these small, intriguing reptiles had a wider distribution across what would have been part of the supercontinent Pangaea during the Triassic. The Connecticut specimen was catalogued under the number AMNH 29300 and included the right side of a skull, several vertebrae, and additional bones that were difficult to identify with certainty. Despite being partial, these fossils were sufficient to recognize features characteristic of Armadillosuchus, confirming that this genus had indeed crossed the Atlantic region of the supercontinent. The fact that the New Haven Formation was deposited during the Nourian stage, slightly after the latest Carnian, suggested that Armadillosuchus persisted for several million years and was able to inhabit different environmental settings across what are now Scotland and the eastern United States. Initially, Armadillosuchus grantii had been classified as part of a group known as Thecodontia. This term, common in early 20th century paleontology, was used to describe a broad assortment of early archosaurs with socketed teeth. However, modern studies have abandoned this category because it was found to be paraphyletic, meaning that it grouped together animals that were not all closely related in an evolutionary sense. Today, scientists prefer to classify Armadillosuchus more carefully within Archosauria, the larger group that encompasses both crocodile line archosaurs, pseudosuchians, and bird line archosaurs, including dinosaurs and pterosaurs. The precise evolutionary position of Armadillosuchus within Archosauria has been a matter of ongoing debate. In the early 21st century, particularly in studies published in the years 2000 and 2002, paleontologists such as Paul Olson and Michael Benton suggested that Armadillosuchus was closely related to Crocodilomorpha, the group that includes all modern crocodiles and their extinct relatives. According to these studies, Armadillosuchus shared a series of unique anatomical features called synapomorphies with crocodilomorphs. Among these characteristics were the medial contact of the maxillae, the upper jaw bones, which formed a secondary bony palate, a feature that helped strengthen the skull. Additionally, Armadillosuchus lacked a postfrontal bone at the top of its skull, and the parietal bones were fused together without any trace of a suture between them. Benton and Walker, in their 1999 and 2002 studies, proposed a new clade named Bathiotica, which united Armadillosuchus with crocodilomorphs based on these shared traits. This suggested that Armadillosuchus might represent an early, basal member of the lineage that eventually gave rise to crocodiles. Despite these early assessments, later studies complicated the picture. In the year 2012, Nesbitt and Butler conducted a more comprehensive phylogenetic analysis, examining a much larger sample of archosaurs from the Triassic period. Their work incorporated Armadillosuchus and compared it with other poorly known reptiles from the same era. They concluded that Armadillosuchus did not fit neatly as a sister taxon to Crocodilomorpha. Instead, they found that it grouped with a rather mysterious reptile called Parringtonia, known from the Middle Triassic deposits of Tanzania in Africa. Together, these two genera were assigned to a family called Armadillosuchidae. However, the precise position of this family within Archosauria remained highly uncertain. In fact, Armadillosuchidae appeared as a polytomy, an unresolved evolutionary branch, at the base of Archosauria, meaning that scientists could not determine with confidence which groups Armadillosuchus and its relatives were most closely related to. This demonstrated that Armadillosuchus occupied a very enigmatic position in the Archosaur family tree, and that our understanding of its evolutionary history remains incomplete. The anatomical features of Armadillosuchus, though fragmentary, provide intriguing clues about its biology and ecology. Like many pseudosuchians of its time, it was likely a small, agile reptile, adapted to a terrestrial lifestyle. The shape of its skull, especially the presence of a robust secondary palate, suggests that it could have had a strong bite, perhaps feeding on small vertebrates, insects, or other invertebrates. The vertebrae associated with the Connecticut specimen indicate that it had a flexible, well-muscled body capable of quick movements, which would have been useful for hunting or avoiding larger predators in the late Triassic ecosystems. While no complete skeleton has been found, these partial remains hint at a small, nimble predator, perhaps no larger than a modern-day fox, which lived in environments that were becoming increasingly complex as the Triassic progressed. The Lossiemouth Sandstone Formation, where the first fossils of Armadillosuchus were found, represents sediments that were deposited in a semi-arid environment with rivers and floodplains. This landscape would have been dotted with small streams, lakes, and perhaps seasonal wetlands, providing habitats for a variety of reptiles, early amphibians, and emerging dinosaur species. The rocks of the New Haven Formation in Connecticut, by contrast, were formed in a similar terrestrial setting but slightly later in time, during the Nourian stage, which means that Armadillosuchus successfully colonized new regions and persisted through environmental changes that occurred over several million years. This longevity and geographic spread demonstrate the adaptability of this small predator within the broader Archosaur radiation of the late Triassic. Fossils such as BMNH, R3139 and AMNE 29300 are crucial not only for understanding Armadillosuchus itself, but also for illuminating broader patterns of reptile evolution in the Triassic. They highlight the diversity of early pseudosuchians and their role in ecosystems dominated by other emerging archosaurs, including early dinosaurs. Although Armadillosuchus may not have been as large or as fearsome as some contemporary predators, it represents an important branch of the archosaur tree, one that helps scientists reconstruct the evolutionary experiments that took place before the rise of the true crocodiles and dinosaurs. Its classification has shifted over time, originally being assigned to the now-defunct group Thecodontia, and later considered a close relative of crocodilomorphs. More recent studies, however, have placed it in a family with the African reptile Parringtonia, demonstrating that its precise evolutionary relationships remain uncertain. Anatomically, Armadillosuchus exhibits a suite of features that hint at a terrestrial agile predator with a strong bite and flexible body. Its fossils offer important insights into the diversity and evolution of early pseudosuchians, highlighting both the complexity of Triassic ecosystems and the enigmatic nature of this small but remarkable reptile.